Hello there, and welcome to Life Beyond Scene, where curiosity is invited to sit down for a while and let the edges of the day soften. Tonight I'd like to take you somewhere we rarely visit in our thoughts, a place that is both close and impossibly far at the same time. You may have walked on a beach before, you may have dipped your toes into the shallow surf or watched the horizon dissolve into a long quiet line, but the world beneath that surface goes further than most of us will ever travel. This journey is about the depths of our planet's oceans, the ultimate valleys of Earth, places so removed from our daily lives that they feel like another world entirely. And yet, they are part of the same planet that holds your home, your streets, your routines. Tonight, we're going downwards, not into the sky, not into the stars, but into the other infinity, the one that begins when the light fades below the waves. It's a strange thing to realise that most of our planet is water, and most of that water lies in regions so deep and so unexplored that even today, in an age when satellites photograph distant planets and probes leave the solar system, we know more about space than we do about our own oceans. There's something quietly humbling about that. We're used to thinking of the world as mapped and measured, every corner charted on Google Maps, every street view available with a swipe. But if you look toward the sea, beneath that moving surface, you're staring at regions we've barely begun to visit. It's like living in a house where most of the rooms are locked, and every time someone opens one, the discovery is a stranger, and more surprising than anyone expected. I wonder, as you're listening now, where you are. Is there water nearby? Maybe a river, a lake, or the sea itself? If not, perhaps only the thought of it, the way it sounds when it moves against a shore, or the way it looks when the sky rests on its surface. And have you ever thought about what's below it all? How far down it really goes? What kind of world lives beneath the waves you see from the surface? As we settle in for this exploration, if you find the thought of venturing into the deep ocean as curious or as calming as I do, it would mean a lot if you gave this little corner of science and rest a like or even subscribed. It helps this space reach others who might enjoy a peaceful way of learning before sleep. And with that, let's begin to lower ourselves gradually into the water, following the fading glow of sunlight as it thins and dissolves into shadow. Imagine standing on the shore and stepping forward until the water reaches your ankles. The sand shifts under your feet. The small waves curl and break against your legs. This is the ocean we know, the one full of swimmers, surfers, and shells. But take one step further, then another, until the ground drops away. You float. You look down, and you realise you can't see the bottom anymore. From there, the descent begins. Sunlight still follows you at first, shimmering and bending, broken into lines that dance like ribbons. Fish dart around in flashes of silver. Plants wave in the slow current. The world is alive with colour, with movement, with familiarity. This is the surface ocean, a place filled with reefs, schools of fish, and life as we usually picture it. But keep going. The deeper you sink, the more the colours change. Red fades first, then orange, then yellow. By about 200 metres down, nearly all warm colours are gone. If you were to hold a red object in front of you, it would look grey, almost black, because the wavelengths of red light can no longer reach this far. Blue remains, faint and cold, the last traveller from the surface. The fish that once shimmered now fade into shadowy silhouettes. The plants that relied on sunlight vanish, because photosynthesis cannot survive without the rays that fuel it. You have left the world of bright reefs and entered what scientists call the twilight zone. Even here, the water is alive with things adapted to the fading light. Many creatures have evolved large eyes, mirrors, or special pigments to catch and use the smallest trace of brightness. Others generate their own. Bioluminescence begins to glow in this realm, tiny sparks of blue-green light blinking in the dark like drifting stars. These organisms don't use sunlight anymore. They carry lanterns within themselves. Some use them to lure prey, others to signal mates, and some simply to confuse predators. A cloud of flashing light can look like a swarm, making it hard for a hunter to pick out just one. Already the rules are different. By the time you reach about 1,000 meters down, the last trace of sunlight is gone. This is where the midnight zone begins. It is a world of complete darkness, endless black stretching in every direction. A place where your eyes would find no horizon and no surface. Pressure builds here in a way that is almost impossible to imagine. At the surface, your body is under about 1 atmosphere of pressure, the weight of the air above you. At 1,000 meters down, the water itself presses with a force nearly 100 times greater. And the deeper you go, the heavier it becomes. At the very bottom, in the deepest trenches, the pressure is over 1,000 times greater than what you feel right now. If you were to suddenly appear there without protection, you would be crushed instantly. And yet, astonishingly, life survives. Some of the strangest creatures on Earth live here. The anglerfish, with its glowing lure dangling in front of jagged teeth. The gulper eel, with a mouth so enormous it can swallow prey larger than itself. The vampire squid, whose name sounds terrifying, but who mostly drifts quietly feeding on detritus, wrapping itself in its cloak-like arms when disturbed. Each of these creatures is shaped by an environment of crushing force and permanent darkness. None of them could survive in our world of sunlight and air, just as we could not survive in theirs. What's remarkable is not only that these animals endure, but that they thrive. They've developed flexible membranes, proteins that resist pressure damage, and metabolisms that function in ways entirely different from ours. For them, the crushing weight is not an obstacle, but simply the background of life. What feels unimaginable to us is ordinary to them. And in that contrast lies one of the humbling truths of nature. Every environment, no matter how extreme, becomes home to something. Lower still, the abyssal plains stretch flat and silent for vast distances. Here, the seafloor is a desert of mud and sediment, occasionally interrupted by jagged volcanic ridges or the slow creep of tectonic plates. Few creatures move across it, but those that do have their own peculiarities. Sea cucumbers glide across the silt like slow travellers. Giant amphipods scavenge what little organic matter drifts down from above. Because that's what fuels much of life here. The constant slow rain of marine snow, tiny particles of organic material falling from the surface, drifting down like silent ash. To us, it sounds meagre, but to the creatures waiting below, it is everything. Eventually, as we continue downward, we reach the deepest places of all, the trenches. The Mariana Trench is the most famous, plunging nearly 11,000 meters, deeper than Mount Everest is tall. To put it in perspective, if you dropped that mountain into the trench, its peak would still be more than a mile underwater. Very few human vessels have ever been down there. The environment is so hostile to machinery that each descent requires years of preparation, and yet, even here, life persists. Small shrimp-like amphipods, snailfish with translucent bodies, microbes feeding on chemicals from the rocks, all surviving in a place that feels less like Earth and more like an alien world. Thinking of all this, you might wonder why it matters to us, why we should care about the creatures in the deepest oceans when we'll likely never see them in person. But consider this. Much of what we've learned about resilience, adaptation, and survival has come from studying these organisms. Enzymes that work under pressure can inspire new medicines and industrial processes. Bacteria that thrive near hydrothermal vents, where hot fluids pour from Earth's crust, have given us insights into how life itself might have begun. In these hidden realms, clues to some of the oldest questions in biology may lie waiting. And as we reflect on all this, let's pause for a moment. Right now, as you listen, your body is light compared to the pressure that exists in the deepest ocean, and yet there are beings alive at this very second enduring that pressure without effort. That quiet fact alone reminds us that the possibilities of life are greater than we usually imagine. The descent is far from finished, We've barely touched the surface of what it means to explore these depths, and the wonders waiting in the darkness are more varied than a single dive can show. But for now, we've begun our journey into Earth's ultimate depths, and from here the story only grows stranger. When you stand on a shore and look out to sea, what you see is a surface, a line that stretches so far it gives the illusion of forever. The horizon itself has a way of drawing the mind outward, making you think of distance, journeys, and possibilities. Yet that line is misleading. It looks like the end of something, when in reality, it is the beginning of a curtain. The surface of the ocean is not a final layer, but a veil. What lies beneath it is not a shallow stage, but an entire universe, more immense than anything we build on land. To think of the ocean as a single body of water is to underestimate its depth, its diversity, and its complexity. What we see when we look outward is only the thinnest slice of what exists. Imagine pulling back that curtain, letting yourself see not only the waves moving in rhythm with the wind, but everything that extends downward from them. For every square kilometre of ocean surface, there is a volume of water beneath that could swallow mountains whole. You could dive for minutes, hours, even days with the right technology, and still never reach the bottom in some places. The curtain hides the largest living space on Earth, a space that covers 70% of the planet's surface and contains 95% of all habitable volume. And yet, we often treat it as if it were a margin, a background, something only important when we swim, fish, or ship goods across it. This curtain does not just cover depth, it also covers distance. From pole to pole, from the Arctic fringes to the equator's heat, the ocean spreads like a single body but never acts as one. The surface may seem uniform, the same blue in every direction, but beneath that colour lie currents, layers, and ecosystems that differ so radically they might as well be separate worlds. In one region, cold dense water sinks, carrying oxygen to the deep. In another, warm surface water lingers, blocking the exchange of nutrients. These invisible movements shape the lives of countless organisms. A fish drifting in the Pacific may find itself carried for hundreds of kilometres by a current it cannot resist, its journey determined by the hidden hand of the curtain beneath. For us, the surface has always been both barrier and invitation. For ancient sailors, the line of the horizon was both the edge of the known world and the promise of something beyond. They saw the curtain but not what lay behind it. Maps were drawn with empty regions marked only with imagination, sea serpents or warnings. Even today, with satellites orbiting above, we still face the reality that vast portions of the ocean floor remain unmapped. The curtain continues to conceal more than it reveals, and that concealment feeds our curiosity. When the curtain parts, what emerges often surprises. Consider the first time humans sent cameras into the deep. Many expected to see emptiness, lifeless mud, and silence. Instead, the cameras returned with images of creatures that seemed pulled from fiction. Transparent jellyfish with bodies like glass, fish with mouths wider than their torsos, delicate creatures trailing filaments longer than a person. The curtain, once pulled back, revealed abundance where we thought there would be nothing. That discovery changed the way scientists thought about habitability. If life could thrive here, in such alien conditions, then perhaps it could exist in other extreme places as well, including beneath the icy shells of moons like Europa or Enceladus. The curtain of our own ocean became a model for curtains elsewhere in the cosmos. Think for a moment about how this curtain also affects us in daily life. The surface waves reflect the sky, so when you look at the sea, you're not only seeing water, you're seeing the light of the atmosphere bent and broken across liquid. The ocean seems blue because of scattering, but it also takes on the mood of the sky. Grey on stormy days, golden during sunsets, dark and glassy under a full moon. The curtain is a mirror, disguising the true colours of what lives below. If you scooped up a bucket from the same sea, you would find it nearly transparent. It is only the curtain of depth that gives the illusion of colour. Within that curtain are countless organisms we rarely think about. At the surface drift plankton, microscopic plants and animals that form the base of the entire marine food web. They are small, fragile, invisible to most of us, and yet they produce half of the oxygen you breathe right now. With every second you spend listening, the breath you take carries the work of organisms hidden in that thin layer beneath the curtain. They have been doing this for hundreds of millions of years, shaping the very atmosphere in which you live. The curtain may look passive from above, but beneath, it is always working, always alive. The curtain also hides a constant rain of life and death. Every day, surface organisms die, fragments of them drifting downward as marine snow. Tiny flakes of organic matter sink through the water column, slowly disappearing into the dark. From the perspective of those living at the bottom, this is not just debris but sustenance. Entire ecosystems depend on this invisible rain. It is the silent link between the curtain above and the abyss below, a bridge of nutrition that sustains creatures who will never see the surface sunlight. This hidden connection works in the other direction too. The deep influences the curtain above in ways we don't often notice. Upwellings, where cold, nutrient-rich water rises, bring with them the building blocks of productivity. These regions become hotspots for fish, birds, and mammals. Without the circulation between the curtain and the depth, the abundance at the surface would fade. The curtain is not simply a separation, it is a living membrane, connecting surface and abyss in cycles that have lasted longer than any civilization. Humanity has always been tempted to pierce the curtain. From the first divers collecting shells and pearls, to modern submarines and remotely operated vehicles, each attempt is an act of curiosity. And each time the curtain is pulled back, we are reminded that we are still beginners here. A diver with modern equipment can descend only so far before pressure forces retreat. Machines can go deeper, but they too are fragile compared to the strength of the ocean. The curtain resists our entry, as if reminding us that not all doors open easily. And yet, the curtain is not impenetrable. Whales have been diving beneath it for millions of years. The sperm whale, for instance, can dive thousands of meters to hunt squid in the darkness, holding its breath for over an hour. Its body is adapted in ways we're only beginning to understand. Its lungs collapse to avoid damage from pressure. Its heart slows to conserve oxygen. Its blood carries enormous reserves of oxygen. These creatures treat the curtain not as a barrier, but as part of their territory. Where we see danger, they see home. Even birds cross this threshold. Shearwaters and petrels skim the curtain's edge, plunging to chase fish that rise from below. To them, the line between air and water is not a wall, but a permeable boundary. In their flight, the curtain becomes a shifting surface, sometimes holding them aloft, sometimes pulling them in. The curtain is different for every species depending on how it is approached. To us, it is mystery. To them, it is daily life. And so, this endless curtain becomes more than a surface. It is a metaphor for limits, for the spaces between what we know and what lies beyond. Every time we peer past it, we find new forms of life, new lessons about resilience, and new reminders of how much remains hidden. The horizon that once looked like an ending becomes a beginning again. If you step back now and picture the ocean not as an expanse of water, but as a layered world, the curtain is just the first threshold. Beyond it lies twilight, then midnight, then abyss. Each level more alien than the last, each filled with organisms adapted in ways that challenge what we thought was possible. And with each step downward, the curtain above becomes thinner in memory until it feels like a distant place, a surface world that has little in common with the darkness below. And as we continue this descent, the curtain fades into distance, and we begin to see what follows. The surface has been left behind. The last of the light has begun to vanish. What lies ahead is the realm where daylight no longer guides life, and new rules begin to take hold. The last traces of daylight sink quickly as we move beyond the surface curtain and deeper into the sea. Up above, the water glimmered with brightness, a constant shifting reflection of sky and sun. But down here, the familiar world thins. The colours that once painted the reefs and shoals fade one by one, as if the ocean has its own way of dimming the lights, lowering the intensity until only fragments remain. By the time we arrive in this region, the world is neither fully light nor fully dark. It is something in between, a band of ocean known to scientists as the Mesopelagic Zone, but more often called the Twilight Zone. It stretches roughly from 200 metres below the surface to about 1,000. That may sound like a neat measurement, but the reality is more fluid. Boundaries here are not strict lines. They are gradients, slow fades where one condition melts into the next. In this zone, sunlight still filters faintly from above, but not enough to fuel photosynthesis. Plants cannot grow here. The energy that once poured from the sun has been thinned to dim threads, like weak beams of light cutting through heavy curtains. If you were to dive without artificial help, your eyes would strain in the gloom. The ocean would appear blue-grey, objects indistinct, distances uncertain. It is an environment of half-light, a world caught permanently between day and night. This half-lit realm is not empty. On the contrary, it may contain more life than anywhere else in the ocean. Billions of tiny fish, squid, crustaceans, and gelatinous creatures inhabit this band, forming one of the largest collective biomasses on the planet. They drift, swarm, hunt, and hide in patterns shaped by the faint glow above and the endless black below. For many species, this zone is both sanctuary and highway. By day, they remain here, hidden from predators. By night, many of them rise upward, sometimes hundreds of meters, to feed on plankton and smaller animals nearer the surface before descending again with the morning. This daily migration, called the DL vertical migration, is the largest movement of animals on Earth, measured not in miles across the land but in vertical climbs and descents that happen every day, unseen by human eyes. Imagine the scene. As darkness falls on the surface, creatures below stir. Tiny crustaceans like krill begin their ascent, joined by lanternfish, bristlemouths, and countless others. Together, they rise in immense numbers, a moving wave of life travelling upward to feed. Then, as dawn approaches, the mass begins its retreat, sinking back into the twilight zone where the dim light hides them from the eyes of predators above. This constant flow is like a heartbeat of the ocean, pulsing every day, driving energy between layers of the sea. Without it, food would not move downward, carbon would not cycle, and the system we depend on for oxygen and climate stability would falter. Many of the creatures here are small, but in their abundance they are powerful. Consider the lanternfish, named for the bioluminescent spots scattered along its body. It is among the most numerous vertebrates on Earth, with an estimated population in the hundreds of trillions. If you could gather all lanternfish together, their collective weight might surpass that of all humans combined. Yet most people have never heard of them, let alone seen one alive. They thrive in the twilight, avoiding bright waters above, and in doing so they maintain an ecological engine far more significant than their size would suggest. Bioluminescence is a defining feature of this realm. In the absence of sunlight, light is produced by the creatures themselves. Bacteria, fish, squid, and jellies all carry chemical systems that generate light from within. The glow serves many purposes. Some use it as camouflage, creating counter-illumination along their bellies so that predators looking upward cannot distinguish their silhouette from the faint light above. Others use flashes to attract mates, long trails of sparks that signal presence in the darkness. Predators use it as lures, like the anglerfish that dangles a glowing bulb in front of its teeth, waiting for prey to mistake it for food. In this zone, light is not just illumination, it is language, disguise, and weapon. The adaptations go beyond light. Eyes here, often outsized, evolved to capture the maximum amount of faint glow. Some creatures have tubular eyes pointing upward, always scanning for silhouettes against the dim surface. Others have mirrored structures to intensify what little light reaches them. Still others, like certain squid, can see polarized light, patterns invisible to our vision but useful for detecting hidden prey. To live here is to be tuned to the edge of darkness, to sense what little remains before it disappears entirely. The Twilight Zone also holds a certain eeriness in its soundscape. While we often think of the ocean as silent, it is in fact filled with vibrations. Whales send out low calls that travel for hundreds of kilometers. Shrimp snap their claws, creating small bursts. Fish drum or croak. In this middle depth, much of that noise mingles, distorted by layers of temperature and pressure. To drop a hydrophone here is to eavesdrop on a chorus of signals, some understood, many not. For creatures who live in the gloom, sound is as important as sight, another way to map and navigate a world where vision has limits. Despite the abundance of life here, this zone has only recently begun to receive scientific attention. For decades, it was overlooked, partly because of the challenges of studying it. It lies too deep for most divers, yet too shallow for deep-sea submersibles that aim for dramatic descents. Nets lowered from ships often miss the more agile creatures, and cameras scare away the most sensitive ones. As a result, much of what we know has come from indirect evidence. Only in recent years, with new technologies like autonomous vehicles and advanced sensors, have we begun to reveal the scale of life hiding here, and each new survey seems to increase estimates of how many organisms call this place home. The Twilight Zone also plays a role in climate that is only now being appreciated. When surface organisms like plankton die or are eaten, their remains or waste often sink into this region. Here, much of it is consumed again, recycled by the countless mouths drifting in the gloom. A portion, however, continues downward into the abyss, carrying carbon with it. This natural conveyor, sometimes called the biological pump, locks carbon away from the atmosphere for centuries or even millennia. Without the Twilight Zone, more carbon dioxide would remain above, intensifying climate change. Thus, the quiet lives of lanternfish and krill influence the very air we breathe. For humans, this region has often been a source of mystery in unexpected ways. During early sonar surveys in the mid-20th century, naval operators noticed a strange false seafloor appearing on their screens. It shifted upward during the night and downward during the day. At first, it was thought to be a solid layer, maybe even an undiscovered seafloor. Later, it was revealed to be the collective bodies of millions of migrating animals, a living layer reflecting sonar beams. This discovery shocked both military and scientific communities. The Twilight Zone was not empty, but alive with movements so vast they changed how sound travelled through the ocean. Even myths may be traced back to this zone. Sailors told of glowing seas, strange lights beneath their ships, or phantom schools of fish shimmering at night. These could easily be explained by bioluminescent swarms rising from the twilight, entire populations glowing in synchronization, visible even from the surface. For those who did not know the science, the effect must have felt supernatural. But even knowing the explanation does not reduce the wonder. To imagine an entire sea glowing from within is to imagine a world where the line between nature and magic blurs. Yet the Twilight Zone is also fragile. Industrial interest has begun to eye this region, particularly as fisheries in shallower waters become overexploited. The immense populations of lanternfish and other species seem tempting as sources of protein or feed. But their role in global cycles is so critical, and our knowledge of their population so limited, that any large-scale harvesting could cause disruptions we cannot yet predict. Protecting this zone means protecting not only its creatures, but also the stability of the systems that connect ocean to atmosphere and life to climate. To picture this zone fully, think of standing in a vast cavern with faint shafts of light filtering through from high above. Around you, creatures drift like ghosts. many glowing, many transparent, all shaped by a world where hiding is survival. Predators lurk, not with speed, but with patience, waiting for a mistake. The water is heavy, cool, and full of unseen signals. It is both abundant and hidden, rich yet elusive. To humans, it remains one of the greatest frontiers not because it is empty, but because it is too full to be easily understood. And as we sink further, the half-light dims completely. Shapes become outlines, then vanish. The last traces of surface brightness dissolve until there is only blackness. Ahead lies the realm of total darkness, where life adapts in ways stranger still. The twilight fades, the midnight begins, and the descent continues. As the faintest glow from the surface gives way to nothingness, the descent enters a region that feels unlike anywhere else on Earth. The twilight fades behind, and in its place is the realm of unbroken night, stretching from about 1,000 meters down to nearly 4,000. Here, no sunlight has ever reached. It is a world defined not by cycles of day and night, but by the permanent absence of either. The surface above could be burning with midday brightness, but down here there is only black. This is the largest continuous environment on the planet, a kingdom of darkness that extends across every ocean basin, encircling the globe, vast beyond imagination and almost untouched by human presence. At first thought, it might seem impossible that anything could live in such conditions. Without sunlight, there is no photosynthesis. Without plants, the foundation of surface food webs vanishes. Without light, vision seems useless. Add to that the crushing pressure, hundreds of times greater than what you experience at sea level, and near freezing temperatures that remain just above the freezing point of seawater, and you have conditions that would kill most known organisms instantly. Yet this realm is not barren. It is populated with creatures so specialized that they appear alien, organisms shaped by darkness into forms and behaviors that are almost unrecognizable compared to the animals we know above. Consider what it means to exist in permanent blackness. Most animals here have abandoned reliance on sight altogether. Some are completely blind, their eyes reduced to vestigial organs. Others have evolved eyes of exaggerated size, capable of detecting the faintest flicker of bioluminescence from many meters away. In either case, vision here is not about colour or shape, but about contrast. Light against dark, motion against stillness. Many species instead use other senses to navigate: lateral lines to detect vibrations, sensitive antennae to feel movement in the water, chemical sensors to smell and taste currents. In this way, the ocean's midnight world is not empty but alive with invisible signals, streams of information carried by touch, vibration, and chemistry rather than by sight. The creatures that inhabit this region are some of the strangest forms of life on Earth. The anglerfish lurks here, famous for the glowing lure that hangs from a fleshy rod above its mouth. The light, produced by symbiotic bacteria, attracts curious prey in the otherwise featureless dark. When the victim approaches, the anglerfish snaps forward with needle-like teeth, swallowing its catch whole. Its jaw is flexible enough to engulf animals nearly as large as itself, because food here is scarce, and any chance at a meal cannot be wasted. Nearby drifts the gulper eel, with a mouth that can balloon like a net, capable of swallowing creatures larger than its own body length. Its tail ends in a glowing organ that it can wave like a lure, tempting smaller fish into range. When prey is near, the eel opens its cavernous mouth, engulfing not only the target but also a large volume of water, straining food from the darkness. The vampire squid, despite its ominous name, is more of a collector than a hunter, gathering falling detritus into sticky threads and consuming the ocean's debris. It carries the appearance of a cloak, turning its arms inside out when threatened, displaying spiny projections to ward off predators. Each of these adaptations may seem bizarre, but they reflect the reality of survival in the midnight realm. Food is unpredictable, arriving either in the form of drifting marine snow from above or in the form of living prey that may pass only rarely. Evolution here has rewarded patience, efficiency, and trickery. Lures, oversized mouths, expandable stomachs, and low metabolisms all serve the same purpose: to make the most of every opportunity in a place where meals may be days, weeks, or even months apart. Not all creatures are large or monstrous. Many are delicate, gelatinous forms like siphonophores, colonies of small specialized individuals linked together to form a single organism that can stretch for tens of meters, glowing faintly in segments as it drifts. Comb jellies move with rows of cilia that scatter light into rainbow patterns, shimmering even in the dark. These creatures are fragile, transparent, and often invisible to predators, yet collectively they form an important part of the food web. Their softness is not weakness, but an adaptation. Bodies made mostly of water are less affected by the crushing pressure around them. Life here has also perfected the art of invisibility. Many fish are black or red, colours that vanish entirely in the absence of long wavelength light. Others are transparent, their organs minimised, their bodies almost indistinguishable from the water itself. Some possess reflective scales, mirrors that scatter light in unpredictable ways, disguising them against the faint background. Predators and prey engage in an endless game of hiding and seeking, each generation refining its methods of deception or detection. Despite its alien feel, this realm is not separate from the rest of Earth. The Midnight Zone is connected to surface ecosystems by the slow rain of organic matter, and it connects further downward to the abyssal plains. It is also home to one of the greatest vertical migrations in nature. As darkness falls at the surface, many creatures rise from this realm into shallower waters, hunting in the relative abundance above before retreating again at dawn. This migration, though driven by hunger, also shapes global systems, moving carbon and nutrients through the water column. In this sense, the Midnight Realm is not only a place of survival, but also an engine of planetary balance. One of the most extraordinary aspects of this zone is its bioluminescence. If you could hover here in darkness and watch, you would see sudden flashes of blue, green, or white, scattered across the water column like distant lightning in a night sky. Some pulses are brief, lasting only a second, while others form drifting trails that linger. These lights are not random. They are communication, defense, hunting tools, or camouflage. A small fish may eject a cloud of glowing fluid to confuse a predator, much like an octopus ejects ink. A squid may pulse brightly to startle an attacker, then vanish into blackness. Some lights are used in coordinated displays, signalling to potential mates. In a place where sight is rare, light has become one of the most powerful forms of interaction. Pressure here is one of the greatest challenges. At 1,000 meters, it is already nearly 100 times what you feel at the surface. At 4,000 meters, it is closer to 400 times. Human technology struggles in such conditions. Metal can deform, glass can shatter, electronics can fail. Yet the creatures here are not only unharmed, but perfectly adapted. Their cell membranes contain special lipids that remain flexible under immense pressure. Their proteins resist denaturation, functioning even when compressed. Many avoid gas-filled spaces altogether, no air-filled lungs or swim bladders, because those would collapse instantly. Instead, their buoyancy comes from oils, fats, or gelatinous tissue. For them, pressure is not an enemy, it is simply part of the environment. The temperature is another constant challenge. Just above freezing, the water here rarely changes more than a degree or two, no matter the season above. This stability creates an environment where life evolves not for flexibility, but for precision. Enzymes are tuned to function in the cold, metabolism slows to conserve energy, and reproduction often occurs at slower rates. Some species may live far longer than their shallow water relatives, their lives stretched out in the slow passage of deep time. Exploring this realm has been one of humanity's most difficult achievements. Very few crewed submersibles have ever reached these depths. Most of our knowledge comes from remotely operated vehicles, deep-sea cameras, and nets dragged upward. Even so, what we see is only a fraction of what exists. Many creatures are destroyed by the pressure change when brought to the surface, their bodies collapsing or expanding in ways that erase their natural forms. Others are too fragile to survive capture at all. As a result, the Midnight Realm remains more mysterious than most of the planets in our solar system. What little we do know continues to surprise. In 2012, scientists exploring with deep-sea vehicles recorded glowing siphonophores longer than blue whales drifting silently in the dark. In other expeditions, they discovered species of fish with transparent heads, allowing their eyes to rotate inside and look upward through their skulls. Each encounter reminds us that the limits of imagination are quickly surpassed by the reality of evolution. There are hints that this realm may also be important for understanding the history of life itself. Hydrothermal vents on the ocean floor, which release mineral-rich fluids into the water, often occur within or just below the midnight depths. Around these vents, entire ecosystems thrive without sunlight, relying on chemosynthesis rather than photosynthesis. Microbes use the chemicals released from Earth's crust as fuel, forming the base of food webs that support worms, clams, and crabs. Some scientists believe that life on Earth may have originated in environments like these, protected from the harsh conditions of the early surface. If true, then the Midnight Realm is not only a place of survival, but also a place of origin, a living museum of possibilities. Yet despite all its richness, this environment also feels profoundly empty to human perception. If you were to float here without light or sound, you might feel as though you were suspended in infinite space. The darkness is absolute, distance is impossible to judge, time itself difficult to measure. It is a world without landmarks, without sun or moon, without the familiar cycles that guide life above. For us, accustomed to light and rhythm, this absence can feel unsettling. For the creatures that belong here, it is simply normal. This difference reminds us of how limited our view of life truly is. We tend to think of our environment, air, land, sunlight, as the baseline, but to the anglerfish, the gulper eel, or the vampire squid, our bright world would be hostile, overwhelming, even deadly. They could not survive in the shallows any more than we could survive in their depths. The Midnight Realm is a reminder that Earth is not one world but many, each shaped by its own rules, each inhabited by beings that see those rules as ordinary. And still, the descent continues. The Midnight Realm, immense as it is, gives way eventually to something deeper still. Below it lies the abyss, a place of silence and weight, where the seafloor spreads out into plains that stretch for thousands of kilometers. From the curtain of the surface to the fading glow of twilight and into the blackness of midnight, the journey is far from over. Ahead, the ocean deepens further, and the pressure rises into extremes beyond imagination. The blackness of the midnight world eventually gives way to something different, though not through the arrival of light. The further down we travel, the more the sense of infinite openness begins to change. In the midnight depths, the water above feels endless, as though the black stretches forever without ceiling or floor. But past 4,000 meters, the seafloor begins to rise into perception. The weight of the ocean is at its greatest here, pressing in from all sides, compressing everything into stillness. This is the abyss, a place where the vastness of water settles against the bed of the earth, where silence deepens into something almost tangible, and where time seems to lose its ordinary flow. The abyssal zone covers more of the planet than any other environment, stretching from 4,000 to 6,000 meters deep, covering the abyssal plains, volcanic ridges, and trenches that span the ocean floor. It is difficult to imagine the scale of this. If you were to smooth out the mountains and valleys of the continents, If you erased the skyscrapers, forests and rivers, what you would be left with would be smaller in size than the abyss. The deep ocean floor is the true face of Earth, yet it is one we almost never see. The silence here is unlike silence on land. On the surface, silence means the absence of familiar sounds, no wind in the trees, no voices, no traffic. But in the abyss, silence is layered with weight. It is not only quiet but heavy, as if the pressure itself has muted the possibility of noise. A stone dropped here would not clatter but sink without comment, swallowed instantly by silt. A whale's call, carried for thousands of kilometres through upper waters, rarely penetrates this far, and even if it does, it is distorted into whispers. For the creatures that live here, sound is minimal, used sparingly and heard only faintly. The world is dominated instead by touch and chemistry, by the gentle drift of currents and the slow fall of matter from above. The creatures that inhabit this silence are some of the most patient on Earth. Many are slow-moving, conserving energy in an environment where food is scarce and unpredictable. Sea cucumbers inch their way across the plains, vacuuming the soft sediment for organic particles. Brittle stars extend their arms into the water, waiting for detritus to land within reach. Deep-sea holothurians, fragile and translucent, float gently above the bottom before settling again. The life here is not dramatic in its movements, but steady, methodical, and persistent. Survival depends not on speed, but on endurance, the ability to continue in a place where resources arrive rarely and irregularly. Occasionally, larger shapes cross the abyss. Deep-sea fish with elongated bodies and huge mouths, specialised to consume anything they encounter, drift slowly in search of prey. Giant amphipods scavenge, their armoured bodies designed for life at crushing depths. Some species of octopus crawl across the bottom, intelligent and adaptable even here, brooding their eggs for years if necessary. Once in a while, the silhouette of a larger visitor appears, sperm whales diving into the deep to hunt, or sharks that can withstand the pressure for short periods. These visits are rare, brief intrusions from shallower worlds. For the most part, the abyss belongs to the creatures that never leave it. What defines this zone most clearly is its pressure. At these depths, every square centimetre of surface experiences hundreds of kilograms of force. A human body would be crushed instantly, a submarine imploded if not designed with extreme precision. Yet for the animals here, this pressure is not an enemy. They have no air-filled spaces, no fragile structures. Their bodies are built to function in compression, with cell membranes adapted to remain fluid and proteins designed to withstand distortion. To us, the abyss is a place of unbearable weight. To them, it is the only normal they know. The cold is equally constant. Near freezing, the temperature never rises, unaffected by seasons or weather above. While the surface ocean shifts with storms and sunlight, the abyss remains steady, its conditions unchanging for thousands of years. To live here is to exist in stability, a stability that forces life into specialization. Enzymes are tuned to exact temperatures. Behaviors evolve for predictable scarcity. Some creatures live far longer than their shallow water relatives, their lives stretched across decades or even centuries. The abyss is not fast. It is slow, deliberate and enduring. Food arrives here mostly from above, in the form of marine snow. This constant rain of organic matter, tiny particles, fragments of dead organisms and waste, drifts downward through the water column, settling finally on the abyssal plains. It is the lifeblood of this environment, fueling everything from microbes to large scavengers. Sometimes larger meals arrive, a fish, a squid, or even a whale carcass sinking to the bottom. These rare falls become ecosystems unto themselves. Scavengers gather first, stripping the flesh within days. Then come smaller organisms feeding on the leftovers, followed by microbes that digest the bones. A single whale fall can sustain life for decades, a sudden windfall in a place of scarcity. For creatures of the abyss, the arrival of such a feast is both unpredictable and transformative. The seafloor here is not uniform. In some places it is flat and featureless, stretching for hundreds of kilometers without variation. In others, it is broken by volcanic ridges, hydrothermal vents, or deep trenches. Each of these features creates unique habitats. At hydrothermal vents, hot mineral-rich fluids pour from Earth's crust, fueling chemosynthetic ecosystems independent of sunlight. Giant tube worms, clams, and crabs thrive here, nourished by bacteria that convert chemicals into energy. These oases of life stand in stark contrast to the surrounding plains, bursts of activity in a landscape otherwise subdued. Trenches, on the other hand, are even deeper scars, cutting into the abyss and reaching into the Hadal zone. The Mariana Trench, for instance, plunges to nearly 11,000 meters, deeper than Mount Everest is tall. At those depths, pressure reaches over 1,000 times that of the surface. Yet even there, life persists. Amphipods, snailfish, and microbes have been found in the Hadal depths, proving that no corner of the ocean is entirely barren. These discoveries remind us that life is not fragile but adaptable, capable of filling every niche available. The abyssal plains are also covered with nodules, strange rock-like formations made of metals that slowly accumulate over millions of years. Manganese, nickel, cobalt, and other elements build layer upon layer until they form potato-sized lumps scattered across the seafloor. These nodules have recently attracted industrial interest, as they contain materials valuable for modern technology. Mining them, however, would disrupt ecosystems we barely understand, stirring up sediments that may take centuries to resettle. The silence of the abyss, once thought secure from human intrusion, now faces the possibility of being broken by machines. One of the most striking things about this realm is the sense of scale it imposes. On land, mountains and valleys define our perspective. In the abyss, the distances are horizontal as much as vertical. A single plane may stretch for thousands of kilometers, a flat expanse with little variation. Imagine walking across a desert with no horizon, no landmarks, no change in terrain. That is the scale of the abyss, magnified by the darkness and silence. It is not only an environment, but an experience of immensity, one that dwarfs human imagination. Despite the scarcity, the abyss is vital to the planet. It acts as a sink for carbon, locking away organic matter that might otherwise return to the atmosphere. It influences global circulation as cold, dense water flows along the bottom, part of the conveyor that connects oceans worldwide. It stores heat, absorbs gases, and moderates climate. In many ways, the abyss is the Earth's memory, holding records of past climates in its sediments, recording changes in chemical balance, and maintaining the stability of the planet's systems. Without it, the surface world would be unstable, vulnerable to rapid swings. The silence of the abyss is not passive but protective, a foundation on which life above depends. Human exploration of this zone has been rare. Only a handful of crewed dives have reached the deepest points, and most of our data comes from robotic vehicles. Every expedition reveals new species, from strange jellyfish with glowing appendages to spiny fish with bizarre morphologies. Each discovery emphasizes how incomplete our knowledge is. We often speak of exploring space as the next frontier, but in truth, the frontier lies just beneath our feet, hidden under the weight of the sea. The crushing silence of the abyss teaches something about resilience. Life here has no abundance, no comfort, no ease, yet it continues, adapted to pressure, darkness, and scarcity. It shows that life is not defined by ideal conditions, but by the ability to persist under any conditions. It also teaches something about humility. For all our technology and exploration, we remain strangers in the largest environment on our own planet. As we drift further across these abyssal plains, the realization grows that this is not an alien world, though it feels like one. It is Earth itself, in its most dominant form. Mountains, forests, and cities cover small fractions of the surface, while the abyss covers most of it. To know Earth fully, one must understand not only the land, but also this immense deep. Yet most of us will never see it, never hear it, never feel the weight of its silence. We live our lives on the thin crust of surface, while below us lies the true body of the planet, silent, heavy, and vast. And still, the journey does not end here. The abyss gives way to other forms, to vents where heat erupts into cold, to trenches that cut deeper still, to ecosystems that thrive without sunlight or surface contact. The crushing silence continues, but within it are voices we are only beginning to hear. Beyond the reach of all natural light, the deep ocean does not give the impression of a place where living things should flourish. Every condition seems hostile. There is no sun to provide energy, no warmth to soften the cold, no familiar rhythm of day and night to guide cycles of activity. The water presses down with enormous weight, oxygen can be scarce, and food does not arrive on a predictable schedule. By the logic of surface life, these depths should be empty, barren, perhaps even sterile. And yet, as we move through the darkness, we find that life not only endures but thrives, in forms that challenge our understanding of what survival means. Where light has failed, life continues with strategies so unusual that they expand the very definition of possibility. The first and most obvious challenge is energy. On land, plants capture sunlight, converting it into chemical energy through photosynthesis. This process supports entire ecosystems, from the smallest insect to the largest mammal. In the deep ocean, sunlight is gone. Without photosynthesis, life must rely on other sources of energy. For much of the deep, that energy arrives in the form of marine snow, particles of organic matter sinking slowly from the surface layers above. Every flake is a remnant of something that once lived in the sunlit world. Plankton, algae, tiny animals, fragments of waste, all drifting downward like ash. Though each particle is minuscule, together they form a steady rain that sustains countless organisms in the dark. But marine snow alone is not enough to explain the abundance of life found in the deep. Larger events also play a role. A dead fish, a shark, or even a whale can sink to the bottom, providing an immense feast in a place of scarcity. These falls transform the immediate environment. Scavengers arrive quickly, hagfish, amphipods, sleeper sharks. They strip soft tissue within days, leaving bones that become habitats for microbes and invertebrates. Over time, specialized communities colonize the remains, breaking down every molecule until nothing is wasted. A single whale fall can support life for decades, becoming an oasis in the otherwise sparse plain. Even more remarkable are the ecosystems that do not rely on sunlight at all, not even indirectly. At hydrothermal vents and cold seeps, chemical energy from Earth's crust fuels entire communities. Here, bacteria perform chemosynthesis, using hydrogen sulfide or methane as energy sources rather than sunlight. These bacteria form the foundation of food webs that support giant tube worms, clams, mussels, shrimp, and crabs. Some tube worms reach 2 meters in length, yet they have no mouth or stomach. Instead, they house symbiotic bacteria inside their bodies, which provide all the nutrition they need. This partnership demonstrates one of the most extraordinary adaptations in biology. Life-forming alliances not with plants or sunlight, but with microbes and chemicals rising from the Earth itself. The vents where these communities thrive are dramatic places. Superheated water, sometimes over 350 degrees Celsius, gushes from cracks in the seafloor, carrying dissolved minerals that solidify into chimneys called black smokers. Around these structures, life gathers in densities unimaginable elsewhere in the deep. Thousands of organisms crowd together, feeding on the energy provided by the vent fluids. The contrast is striking. In the surrounding plain, life is sparse and spread thin. But near a vent, The seafloor becomes crowded, noisy with activity, bursting with growth. When one vent shuts down, the community collapses, but elsewhere another may form, continuing the cycle. Life here is not stable in the sense we know it, but it is resilient, able to flourish wherever conditions arise. These discoveries overturned long-held assumptions about biology. Before scientists found vent communities in the 1970s, most believed that all life ultimately depended on the sun. The revelation that organisms could survive entirely independent of sunlight expanded the search for life elsewhere in the universe. If microbes and animals could thrive in the dark depths of Earth, fueled only by chemistry, then perhaps life could also exist in the subsurface oceans of icy moons, or in underground environments of distant planets. The deep ocean showed that life's boundaries were broader than anyone imagined, but survival here is not just about finding food, it is also about enduring conditions that would seem unlivable. Pressure increases dramatically with depth. At 6,000 meters, it is 600 times greater than at the surface. For most surface organisms, such pressure would crush cells, denature proteins, and disrupt essential processes. Deep-sea creatures avoid these effects through molecular adaptations. Their proteins are built with structures that resist pressure-induced changes. Their membranes contain unique lipids that remain fluid even under compression. Many avoid any gas-filled cavities, lungs, swim bladders or sinuses that would collapse at depth. Instead, buoyancy is maintained with oils, fats or gelatinous tissue. To them, the crushing weight is simply background, as ordinary as gravity is to us. Temperature is another constant factor. In most of the abyss, water hovers just above freezing, between 1 and 4 degrees Celsius. Such cold slows metabolism, slows growth, and extends lifespan. Many deep-sea species grow slowly, reproduce infrequently, and live much longer than their shallow water relatives. Some may survive for centuries, moving through time with a pace that is alien to our fast-lived lives. Others may delay reproduction for years, waiting until conditions allow. This slowness is not weakness, but adaptation, a way to survive where energy is scarce and conditions are stable. Predation and defense also take unusual forms here. In the absence of light, camouflage becomes a matter of invisibility. Many organisms are transparent, their tissues letting light pass through to reduce visibility. Others are covered in light-absorbing pigments, rendering them black against the darkness. Some are red, a colour invisible in the absence of red light at depth. Others use bioluminescence not just for attraction but for defence. A startled squid may eject a glowing cloud of light, confusing predators and allowing escape. Some fish flash their lights in rapid pulses, disorienting attackers. In every case, the strategies are shaped by the absence of sunlight, by a world where vision works differently. Communication takes forms we can only partly understand. Light signals are one method, but chemical cues also play a role. Many organisms release pheromones into the water to attract mates or signal presence. Some use vibrations or sounds, faint pulses detectable across short distances. In the vast emptiness of the deep, finding a mate is a challenge, and species have evolved unique ways to solve it. Some anglerfish, for example, engage in a strategy where the much smaller male fuses permanently to the female's body, merging bloodstreams and ensuring constant availability. To us, this may seem extreme, but in the scarcity of the deep, it is an effective guarantee of reproduction. The persistence of life where light fails also carries lessons about the origins of complexity. The transition from microbial life to multicellular organisms required cooperation, communication, and adaptation. In the deep, we see examples of how such cooperation can thrive under difficult conditions. Symbiosis between bacteria and animals, between microbes and vents, shows that life builds relationships even when isolated from familiar energy sources. Complexity does not require abundance, it requires ingenuity. The persistence of life here also reveals the interconnectedness of Earth systems. Deep-sea organisms play roles in regulating global cycles. By consuming falling organic matter, they control how much carbon is stored in the seafloor sediments. By circulating nutrients, they influence the chemistry of the ocean. Hydrothermal vent microbes recycle elements essential for life, such as sulfur and nitrogen. In this way, the unseen deep helps sustain the balance of the surface world. What seems remote and irrelevant is in fact central to the functioning of the planet. It is worth pausing to consider how little of this we would know without modern exploration. For centuries, the deep ocean was assumed to be lifeless, a desert of mud. Even in the early 20th century, many scientists doubted that complex life could exist at great depths. It was only with the invention of deep-diving vehicles, remotely operated robots, and advanced sensors that we began to glimpse the reality. Each new expedition continues to reveal forms of life never before seen, each adapted in ways that defy expectation. The deep ocean remains Earth's greatest wilderness, a place where discovery is guaranteed not because we search so thoroughly, but because we search so little. For all its strangeness, the persistence of life in darkness also carries a familiar echo. Just as organisms here find ways to survive without sunlight, humans too adapt to environments that seem inhospitable. From deserts to frozen tundras, from mountaintops to crowded cities, our species has learned to persist in extremes. In the deep ocean, however, the scale is far beyond anything we endure. It reminds us that the resilience of life is not uniquely ours. It is a shared quality, spread across the tree of life, present wherever conditions allow. The persistence of life where light fails also invites a certain humility. We tend to associate life with comfort, with familiar conditions, with the presence of sun and warmth. The deep shows us that life does not require those things. It can thrive without them, finding energy in chemistry, protection in pressure, and community in scarcity. In this way, the deep is both alien and profoundly earthly, a mirror of possibility reminding us that survival is less about environment and more about adaptation. As we continue this journey downward, past the abyssal plains and into the deepest trenches, the story of persistence becomes even more remarkable. The Hadal depths push conditions further, intensifying pressure to levels beyond imagination. And still, life is there, hidden but enduring, proving again that Earth's ultimate depths are not empty, but alive. In the absence of sunlight, one of the most remarkable solutions life has discovered is to make its own illumination. The deep ocean is not a place where beams of natural light reach, but it is far from entirely dark. Here, thousands of species have evolved the ability to glow. They are not reflecting light from above, but producing it chemically within their own tissues. This phenomenon, called bioluminescence, is so common in the deep that some researchers estimate the majority of mid-water organisms are capable of it. The blackness is alive with flashes, glows, and signals that are invisible to us from the surface. But down here form an entire language of survival. What makes this light so unusual is that it arises from chemistry, not heat. On land, we are used to light being produced by fire, electricity, or heat filaments. These require energy losses and can be wasteful. Bioluminescence, by contrast, is cold light. Through a reaction between molecules known as luciferin and enzymes called luciferase, organisms can generate illumination without significant heat. In many species, the light is produced by symbiotic bacteria housed inside specialized organs. In others, it is generated directly by the animal's own chemistry. The result is a system that allows control, flashes, pulses, steady glows, or even complex patterns. The colours of these living lanterns are almost always shades of blue and green. This is not random. Water absorbs most wavelengths of light, with red disappearing quickly, followed by orange and yellow. Blue travels furthest, making it the most effective signal in the deep. As a result, the ocean's lanterns almost universally emit in this range. A few rare species, however, produce red or even infrared light, giving them an advantage in communication that other species cannot detect. To those with the right vision, red bioluminescence becomes a secret code, invisible to predators and prey alike. The purposes of this light are as varied as the creatures themselves. One of the most important uses is camouflage. This may sound counterintuitive, since light seems to make an animal more visible. But in the deep, predators often hunt by looking upward, searching for silhouettes against the faint glow filtering down from above. Many species counter this by producing light on their undersides, matching the brightness of the surface glow. This technique, called counter-illumination, erases their shadow and renders them nearly invisible. Squid, shrimp and fish alike employ it, adjusting their brightness in real time to mimic the dim surface light. Others use bioluminescence for defense. Some fish eject glowing mucus when threatened, creating a sudden burst of light that confuses predators. A few squid release luminous clouds instead of ink, momentarily dazzling attackers before vanishing into darkness. Some deep-sea worms produce glowing green sparks when disturbed, breaking apart into glowing fragments that distract anything nearby. Even small crustaceans have been observed releasing light-filled bubbles, buying just enough time to escape. In a world where predators often strike from unseen angles, the ability to blind, confuse or distract with light can mean the difference between life and death. For predators, bioluminescence is an equally powerful tool. The anglerfish is perhaps the most iconic example, dangling a glowing lure in front of its mouth. Curious prey, mistaking the glow for food, approach too closely and are swallowed whole. Other species employ more subtle tactics. Some dragonfish, for instance, have barbel-like extensions tipped with glowing bulbs, which they flicker enticingly while remaining motionless. Their mouths, filled with sharp teeth, close around victims that mistake the light for a harmless drifting organism. But light is not only for deception, it is also for communication. In the emptiness of the deep, finding a mate can be difficult. Populations are sparse, distances vast, and encounters rare. Many species solve this by flashing unique patterns of light, a kind of signature that identifies species and even individual sex. Male and female lanternfish, for example, often differ in the arrangement of their photophores, the small organs that emit light. These patterns allow recognition in the dark. In some species, synchronized flashing creates a kind of luminous courtship dance. In others, the display is subtle, a single glow pulsing at intervals until another responds. For animals spread thin across immense spaces, light becomes a bridge, bringing them together despite the darkness. Entire swarms of organisms sometimes glow at once, producing displays visible even from the surface. Sailors throughout history have described nights when the sea itself seemed to shine, glowing with a soft blue-green radiance. What they witnessed were countless plankton, disturbed by waves or ships, releasing light in unison. The spectacle can stretch for kilometers, transforming the ocean into a rolling field of illumination. To those who saw it without explanation, it must have seemed supernatural. To us it remains no less astonishing, a reminder that the ocean is capable of beauty far beyond anything we orchestrate on land. The diversity of organisms that glow is staggering. Tiny bacteria, free-floating plankton, jellyfish, squid, shrimp, fish, and even some sharks possess bioluminescence. Each has its own variation on the theme. Some produce steady glows, others rapid flashes, still others shifting waves of light across their bodies. Certain comb jellies scatter light not through chemical means, but by refracting it along their cilia, creating rainbow effects that shimmer as they move. The result is a tapestry of living lanterns, each species contributing its own signal to the deep. The sheer prevalence of bioluminescence suggests that it is not an optional trait, but a central feature of survival in the deep sea. In fact, some scientists believe that more organisms in the ocean are bioluminescent than not. This means that what we think of as unusual may actually be the norm. It's only unusual from our perspective because we live in a world dominated by sunlight. In the deep, where light fails, making your own glow is the default. The study of these organisms has also begun to influence human technology. The luciferase-luciferin system used by glowing creatures has been adapted in laboratories for medical imaging, genetic research, and environmental monitoring. By attaching the genes responsible for bioluminescence to other cells, scientists can track processes inside living bodies, detect toxins, or visualize patterns invisible otherwise. The same chemistry that keeps deep-sea animals alive is now guiding advances in human medicine. Even beyond science, bioluminescence has shaped culture. Myths of glowing seas, tales of ghostly lights beneath ships, and stories of fiery waters all trace back to encounters with living lanterns. Before we understood their cause, they were woven into legends. Even now, when we can describe the chemistry, they retain a sense of wonder. Watching a beach at night come alive with glowing waves stirred by footsteps still feels like magic. The knowledge of enzymes and molecules does not erase the experience of standing in awe before living light. One particularly striking adaptation can be found in certain deep-sea dragonfish. These predators produce not only blue light, but also red, invisible to most other species. They can see in this wavelength, allowing them to use red light like a private torch, illuminating prey without being detected. To the prey, the darkness seems complete. To the dragonfish, the glow reveals everything. It is a one-sided advantage, a perfect adaptation in a world where visibility is rare. There are also species that can modulate their light intensity with precision. Some lanternfish adjust their counter-illumination to match shifting surface brightness, dimming as clouds pass overhead or brightening under moonlight. Others use rapid flashes to create patterns that disorient predators, like a strobe effect in the dark. Still others pulse rhythmically, creating signals that may carry meaning we have yet to decode. For us, light is mostly about seeing. For them, it is an entire vocabulary, flexible and expressive. What becomes clear is that in the absence of sunlight, light itself becomes the currency of survival. It is the means by which animals hide, hunt, communicate and attract. It transforms the deep from a realm of emptiness into a stage of signals, each flash and glow carrying intention. Without bioluminescence, the deep would indeed be barren. With it, the blackness becomes alive, filled with stories written in light. And yet these lanterns do not make the deep any less challenging. They illuminate, but they do not banish the pressure, the cold, or the scarcity. They do not turn night into day. Instead, they carve out narrow advantages, brief moments of visibility, or fleeting connections in the dark. They are adaptations, not miracles, and they exist because life in the deep is difficult. In that difficulty, creativity flourishes. Each glow is a solution, a testament to the fact that survival is not about abundance, but about invention. As we move deeper still, past the lantern-filled midwaters and toward the plain of the abyss, the role of bioluminescence continues, but new forms of adaptation emerge as well. The seafloor introduces different challenges, from stability to scarcity, and creatures meet them with their own ingenuity. The living lanterns fade into distance, but the persistence of life continues to shape the silence in new ways. The deeper one goes, the more it becomes clear that the deep ocean is not only inhabited by strange creatures, but also constructed by them. Down here, survival often depends not simply on drifting or feeding, but on shaping the environment itself. Even in the absence of sunlight, with crushing pressures and temperatures near freezing, some organisms create structures that alter the landscape, turning emptiness into habitats. They are the architects of the deep, builders that design in mud, rock, and even in living tissues, crafting spaces where communities can exist that would otherwise be impossible. One of the most striking examples comes from corals, though not the shallow water corals most people know. In the dark depths, cold water corals grow without the need for sunlight or photosynthetic algae. They spread across ridges and seamounts, forming intricate reefs that stretch for kilometres. These reefs are not brightly coloured like tropical corals, but pale and ghostly, sculpted into branches and frameworks that rise from the seafloor. Over centuries, they grow into massive structures, creating shelter for fish, crustaceans, and countless smaller organisms. Where the seafloor might otherwise be flat and featureless, these reefs bring height, texture, and complexity, transforming emptiness into a thriving community. Similarly, sponges take on the role of builders. In the deep, sponges are not just soft-bodied filters. Some species grow into towering formations, their silica skeletons forming intricate lattices that resemble delicate glasswork. The so-called glass sponges, with their fragile yet resilient structures, filter vast amounts of water, extracting food particles too small for most other creatures. In doing so, they also provide shelter for small fish and invertebrates, who find safety in their porous frameworks. Some sponge reefs have been discovered stretching for hundreds of kilometres, silent cities constructed from living crystal. Tube worms also shape the landscape. Around hydrothermal vents and cold seeps, giant tube worms anchor themselves in dense clusters, their long bodies packed together so tightly that they form living pillars. Each worm hosts symbiotic bacteria that convert chemical energy into food, and together they create ecosystems rich in life. These towering colonies alter the chemistry of the water around them, concentrating nutrients and supporting hundreds of other species. Where vents emerge, the worms are among the first settlers, their growth paving the way for a cascade of other organisms. Even smaller architects play roles here. Deep-sea microbes build mats across the seafloor, weaving filaments and colonies that trap sediments, stabilize the ground, and provide surfaces for others to colonize. These mats can cover wide areas, turning otherwise barren plains into layered living carpets. They may not look dramatic to human eyes, but they create foundations for entire food webs. Without these microbial architects, many other species would struggle to find a foothold. Some of the strangest architecture is not built from minerals or tissues, but from mucus. Lavaceans, small tadpole-like animals, construct elaborate mucus houses around themselves, structures that act like filters to capture microscopic food. These houses can be surprisingly large compared to the animal, and when clogged with particles, the lavacean abandons them and builds a new one. In the deep, abandoned mucus houses rain down like jelly balloons, becoming food and habitat for other organisms. The cycle of construction and abandonment contributes significantly to the movement of organic matter through the depths. These fragile structures, invisible at the surface, are vital architecture on a microscopic scale. Creatures like crabs and shrimp also modify their surroundings. Some dig burrows into the sediment, creating tunnels and chambers that offer refuge from predators and currents. These burrows also mix the sediment, redistributing nutrients and oxygen in ways that benefit other organisms. Over time, entire landscapes of pits, mounds, and tunnels form, shaped not by geological processes but by the cumulative work of small animals. The seabed becomes textured, full of hidden architecture invisible without careful study. Then there are the shell builders. Many deep-sea mollusks, though living in scarcity, still create shells of calcium carbonate. When these shells accumulate over millions of years, they form layers of sediment that shape the ocean floor. In this way, even the smallest architects leave a geological legacy, slowly writing their presence into the planet's crust. Perhaps the most dramatic architects, however, are the bacteria and microbes around hydrothermal vents. By metabolizing chemicals like hydrogen sulfide, they precipitate minerals that build the towering chimneys of black smokers. These chimneys, sometimes tens of meters tall, are entirely constructed by microbial processes. They rise like castles from the seafloor, venting superheated fluids into the cold abyss. Around them, communities flourish, supported by the bacteria that built the towers in the first place. It is architecture on a scale both tiny and massive. microscopic organisms assembling monumental structures that host entire ecosystems. The work of these architects has consequences beyond simple shelter. By creating reefs, mats, chimneys, or burrows, they alter the flow of water, the distribution of nutrients, and the availability of habitat. They increase biodiversity by providing niches for other species. They influence chemical cycles by trapping or releasing elements. They even affect geology, as their structures become fossilized over time, preserved in sediments for millions of years. In this way, the architects of the deep are not just survivors but shapers, active participants in the design of their world. To appreciate their role, consider what the deep would be without them. Imagine only mud and flat plains, a landscape with little variation. Life would exist, but sparsely, with few places to hide or attach. Predators and prey would meet in a barren arena. Instead, thanks to the builders, the deep is full of variety. Coral forests, sponge towers, worm pillars, and bacterial mats break the monotony, turning the seafloor into a patchwork of habitats. Each structure creates new opportunities, and in turn more life emerges. Even the fragile temporary constructions matter. A lavation's mucus house may last only hours, but in that time it filters vast amounts of water and provides food when discarded. A crab's burrow may collapse, but while it exists it shelters countless microorganisms. The deep is shaped not only by grand architecture but by constant small efforts, each adding up to a landscape in motion. What is striking is how often this architecture arises not from deliberate design but from necessity. Corals do not build reefs to provide homes for others. They simply grow, and in doing so they create shelter. Worms cluster because it helps them survive near vents, and the cluster becomes habitat. Microbes form mats for their own stability, and the mats become foundations for ecosystems. Architecture here is a byproduct of survival, yet it serves the larger community. In this way, the deep demonstrates a kind of unplanned cooperation, where individual adaptations combine to shape environments for many. For us, these architects hold lessons. They show that environments are not only given but made, that survival can involve changing the surroundings as much as adapting to them. They remind us that life shapes Earth, not just passively but actively, through construction, alteration, and legacy. The deep is not just a setting for life. It is a canvas continually rewritten by its inhabitants. As the journey continues, the role of these architects becomes even more apparent. Further down, in the trenches and at the margins of the abyss, structures take new forms, shaped by pressure, chemistry, and scarcity. The deep is not static but dynamic, built and rebuilt over time by the countless architects who persist where light never reaches. The deeper we travel, the more one reality becomes unavoidable: pressure. It is not only a condition here, it is the defining force of the deep ocean, an invisible weight that dictates the shape of every creature, the form of every adaptation, and the limits of exploration. Above, on the surface, we think of the ocean as open and limitless, but beneath that calm veil is a gradual accumulation of force so extreme it becomes hard to compare with anything on land. Pressure is not a background detail in the depths, it is the very medium through which life must move. At the surface, we live under one atmosphere of pressure, the weight of the air above us pressing down evenly across our bodies. It is so familiar we never notice it. But water is much denser than air, and as you descend it adds rapidly. For every 10 meters the pressure increases by another atmosphere. At 100 meters you experience 10 times the surface pressure. At 1,000 meters the force is 100 times greater. At the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure exceeds 1,000 times what we know on land. Imagine the weight of 50 jumbo jets resting on a single human body. That is the scale of the forces pressing on life at those depths. For us, unprotected, this pressure is lethal. Our lungs would collapse, our blood vessels rupture, our tissues compressed beyond survival. Submarines not engineered for such depths implode violently, crushed as though they were made of paper. Steel bends, glass shatters, and even the smallest flaw in construction can mean destruction. And yet, astonishingly, life here does not just survive. It is perfectly at home. Creatures move through this pressure with no awareness of its danger, their bodies so adapted that what would destroy us is nothing more than the air they breathe. The solutions life has evolved to endure this weight are extraordinary. The most obvious is the absence of gas-filled spaces. Lungs, bladders and cavities cannot exist here, as they would be compressed instantly. Instead, animals rely on oils, fats and gelatinous tissues to provide buoyancy and shape. Fish that in shallower waters carry swim bladders, air-filled organs for balance, abandon them at depth. They replace them with wax esters or lipids that are unaffected by pressure. Their bodies become less rigid, more flexible, able to withstand compression without damage. At the microscopic level, adaptations are just as striking. Cell membranes in deep-sea organisms contain unique lipids that remain fluid under immense compression. Their proteins are built with structures that resist distortion, preventing them from collapsing or unfolding under stress. Special molecules, known as piezolites, accumulate in their cells, stabilizing proteins and enzymes so they continue to function even when pressure distorts chemical bonds. These adaptations may seem invisible, but they are the difference between life and death in the abyss. Pressure also influences behavior and physiology. Many deep-sea animals have extremely slow metabolisms, conserving energy in conditions where movement and activity are costly. Their muscles may be weak by surface standards, their activity limited, but this suits an environment where food is scarce and pressure constant. Reproduction is often slow, growth gradual, lifespans extended. Pressure shapes not only the body but the very rhythm of life. Even vision is affected. Eyes that might collapse or distort under compression evolve into new forms. Some creatures reduce their eyes entirely, abandoning sight as a primary sense. Others develop reinforced structures, tubular designs, or specialized lenses that continue to function despite the weight pressing against them. In some, vision narrows to detect only faint bioluminescent signals, trading broad perception for precision. Pressure does not simply crush, it sculpts. From our perspective, the most humbling truth is that these adaptations are not extreme to the animals themselves. To them, the crushing weight is as ordinary as gravity is to us. They do not notice it. They do not fight it. They simply exist within it. Their bodies shaped from birth to thrive in a medium we cannot imagine surviving. This reversal of perspective, what is impossible for us being ordinary for them, illustrates the relativity of environment. What is hostile to one form of life is home to another. For humans, pressure has been one of the greatest barriers to exploration. Early attempts to reach deep waters relied on steel hulls and reinforced vessels, but even the strongest designs had limits. The bathyscaphe Trieste, which reached the Challenger Deep in 1960, carried walls of steel over 12 centimetres thick and a small sphere barely large enough for 2 men. Even then, the viewing windows cracked under the strain. Modern submersibles equipped with titanium hulls and advanced composites still face immense challenges. At extreme depths, every component must be engineered with precision. Even slight imperfections can result in catastrophic implosion. Remote vehicles fare somewhat better, but they too face limitations. Electronics must be protected, cameras shielded, cables reinforced. Pressure infiltrates everything, demanding careful design. Yet despite these challenges, exploration continues, driven by the promise of discovery. Every descent reveals new species, new adaptations, and new evidence of life's resilience. For engineers, pressure is a hazard. For biologists, it is a sculptor, a force that has shaped entire ecosystems invisible to the surface world. Pressure also influences the chemistry of the ocean. At great depths, gases behave differently, dissolving more readily in water. Oxygen, carbon dioxide, and methane interact in ways that alter ecosystems. Microbes exploit these conditions using chemical reactions unavailable in shallower waters. Hydrothermal vents, under extreme pressure, release fluids at temperatures that would boil at the surface but remain liquid here. The combination of pressure and chemistry creates habitats that are not only survivable, but rich in energy. Without pressure, these ecosystems would not exist. The psychological effect of imagining such pressure is also profound. To think of being suspended in a world where the water around you carries the weight of mountains is to feel a certain unease. Humans are not built to sense pressure changes beyond a few atmospheres, and so the scale of it at depth is alien to us. We can calculate it, measure it, simulate it, but we cannot truly feel it. For the animals that live there, it is invisible, unnoticed, unremarkable. What terrifies us does not even register to them. Some of the most surprising evidence of adaptation comes from trench-dwelling creatures. Amphipods collected from depths over 10,000 meters contain unique biochemicals that allow their cells to withstand immense compression. Snailfish discovered in trenches appear delicate, almost translucent, yet they thrive in conditions where human technology struggles to endure even briefly. These species prove that life's capacity to adapt extends beyond what theory alone might predict. Pressure, once thought to be an absolute barrier, is shown to be another parameter life can accommodate. Pressure has also inspired new questions about the origins of life. Some researchers propose that early life on Earth may have emerged under high-pressure conditions, perhaps in the deep ocean or beneath layers of ice. If so, then pressure is not only survivable, but may have been essential. The molecular stability it imposes, the unique chemistry it enables, could have fostered the first biological reactions. In this sense, the crushing weight of the deep is not simply an obstacle, but a possible cradle. For those who venture into these depths with machines, the experience of pressure is not only a scientific challenge, but an existential reminder. Every creak of a hull, every groan of metal, every shudder of a window reminds explorers of the immense force outside, and yet, for the life surrounding them, this is no burden. It is the ordinary state of existence. The contrast is stark, human fragility against the quiet endurance of deep-sea creatures. As we move further into these depths, pressure remains constant, unrelenting, shaping every organism and every process. It is not a phase to be passed through, but the permanent condition of life in the deep. The architects, the lantern bearers, the scavengers, the hunters, all exist under this invisible weight. And ahead, as we travel into even stranger realms of the ocean, pressure continues to write its influence, dictating forms of life we have only begun to glimpse. In the deep, where pressure is constant and light has vanished, survival takes on an entirely different character. Food is never abundant, meals arrive unpredictably, and energy cannot be wasted. For creatures that live here, every movement must serve a purpose. Every adaptation must increase the odds of success. Among them are the hunters, predators who stalk or wait in the blackness, unseen until the moment they strike. They are the unseen hunters of the deep. Creatures evolve to exploit every weakness, every flicker of light, every movement against the stillness. Their weapons are not speed and strength alone, but patience, deception, and efficiency. Predators of the deep must solve a unique problem. In shallower seas, prey can be seen, chased, or ambushed using vision. In the black depths, sight is often useless. Instead, hunters rely on alternative senses. Some detect faint vibrations through highly sensitive lateral lines, picking up the ripples of swimming prey. Others use smell and taste, detecting chemical trails invisible to us. A few produce their own light, creating lures or strobes that confuse or attract. Each strategy reflects the challenge of hunting in an environment where nothing can be seen clearly, and every action is muffled by silence. One of the most iconic hunters here is the anglerfish. With its gaping mouth lined with needle-like teeth and its glowing lure, it is the embodiment of predation in the dark. It does not chase its prey, it waits. The bioluminescent lure dangles just in front of its face, pulsing or drifting like a small drifting organism. Curiosity brings smaller fish close, and in a split second, the anglerfish snaps forward, swallowing the victim whole. Its jaw is so flexible it can engulf prey nearly half its size, and its stomach can expand to hold the catch. In a world where the next meal may not come for weeks, the ability to eat anything available is essential. Another formidable hunter is the gulper eel. Its body is long and serpentine, but its most striking feature is its mouth, which can open like an enormous pouch. The gulper eel's jaw is larger than the rest of its body, allowing it to scoop up prey of remarkable size. Its tail ends in a glowing organ, which it waves to attract attention. When an unsuspecting animal approaches, the eel opens its cavernous mouth, sucking in both prey and water, filtering the catch before releasing the excess. It does not rely on precision but on volume, a strategy that maximizes success when encounters with prey are rare. Dragonfish are another line of unseen hunters. Sleek and elongated, they are armed with long teeth that resemble needles. Some species carry barbell-like appendages tipped with glowing lures, which they dangle in front of them while remaining still. They possess the rare ability to produce red bioluminescence, invisible to most other deep-sea creatures. Using this hidden light, they illuminate prey without being seen, giving them a private searchlight in the dark. Their eyes, tuned to detect red wavelengths, reveal victims that have no idea they are visible. It is a stealth technology unmatched by most predators on Earth. The hatchetfish, though smaller, employs a different tactic. Its body is flattened and covered with reflective scales that scatter any light, making it nearly invisible from the side. Along its belly, rows of photophores produce counter-illumination, erasing its silhouette when viewed from below. To prey, the hatchetfish is invisible until it strikes. Its large eyes, pointing upward, detect the faintest glow of bioluminescent organisms above, guiding it toward opportunities. For an animal barely a few centimeters long, these adaptations turn it into an effective hunter in an unforgiving environment. Not all hunters rely on light. Some sense movement with extraordinary sensitivity. Certain squid can detect vibrations carried through the water, pinpointing the exact location of swimming prey. They launch forward with tentacles lined with hooks or suckers, seizing victims before pulling them into parrot-like beaks. Their strikes are sudden, explosive bursts of speed in a world otherwise defined by stillness. Once caught, prey has little chance of escape. Sharks, too, inhabit the deep. Species like the six-gill shark, the sleeper shark, and the goblin shark are adapted for hunting in darkness. They move slowly, conserving energy, but can strike with speed when necessary. Their sensory systems detect electrical signals produced by the muscles and nerves of prey, allowing them to locate animals hidden in the sediment or invisible in the black. The goblin shark, with its extendable jaw, can launch its mouth forward like a spring, snatching prey with startling suddenness. These hunters remind us that even ancient lineages have found ways to thrive in the deep. The strategy of many hunters here is not pursuit but patience. Energy is too scarce to waste in long chases. Instead, ambush and deception dominate. A predator may remain motionless for hours, even days, conserving energy until the right opportunity arrives. When it does, the attack is swift and final. In this way, hunting is not a constant activity, but an intermittent one, punctuated by rare but decisive moments. There are also hunters so delicate and strange they defy easy description. Siphonifers, colonies of small organisms linked together, can extend for tens of meters, drifting like translucent threads. Some deploy long stinging tentacles that hang downward, ensnaring prey that swims unknowingly into them. These tentacles can deliver venom powerful enough to paralyze, pulling victims upward toward the colony. To us, the siphonophore seems like a single creature, but it is actually many, each specialized for a task, some for floating, some for digestion, some for reproduction. Together they form a living trap, a drifting predator that requires no chase. Hunting in the black also extends to scavenging, which in the deep often blends seamlessly with predation. Amphipods, shrimp-like crustaceans, gather in swarms when a large carcass sinks. They strip flesh quickly, their jaws tearing through tissue with astonishing efficiency. To them, a dead whale is no less valuable than live prey, and their ability to arrive in massive numbers turns them into formidable forces. For large scavengers like sleeper sharks, a whale fall is both a meal and an opportunity to dominate smaller competitors. In the deep, the line between hunter and scavenger blurs. Every available resource is taken, whether alive or dead. These unseen hunters are not reckless. Their existence is built on restraint, on strategies that maximize energy while minimizing waste. Their adaptations show that survival in the black is not about endless aggression, but about timing, efficiency, and precision. A single strike may determine survival for weeks. A missed opportunity may mean starvation. In this sense, the deep hunters embody a kind of patience rarely found on land. From our perspective, their appearance often seems monstrous. Anglerfish with gaping jaws, dragonfish with fangs longer than their heads, eels with balloon-like mouths. These forms look grotesque when seen out of context. But in their world, each feature is logical, each exaggerated structure a perfect solution to the constraints of the deep. What seems terrifying to us is simply practical to them. For the prey species, survival depends on counter-strategies. Many are transparent, making them difficult to see even with bioluminescent searchlights. Others migrate vertically, rising at night to feed and sinking by day to avoid detection. Some release glowing decoys when attacked, forcing predators to choose wrongly. This constant arms race ensures that hunters evolve sharper tools, while prey evolves better defenses, neither side ever fully victorious. Exploring this realm has revealed only glimpses of these hunters in action. Cameras capture brief encounters, a dragonfish swallowing a smaller fish, a gulper eel inflating its enormous mouth, a siphonophore extending its stinging net. Each sighting adds a piece to the puzzle, but the full picture remains hidden. The vastness of the deep ensures that most hunts happen unseen, in silence, witnessed only by the participants themselves. Yet the evidence of predation is everywhere. Scarred bodies, partially eaten prey, sudden bursts of bioluminescent light fading into darkness, all testify to the constant presence of hunters. Even when invisible, their influence shapes behavior. Prey species remain cautious, conserving energy, avoiding open water. Movements are restrained, purposeful, never careless. The presence of hunters, though unseen, dictates the lives of everything around them. In many ways, the unseen hunters of the black are reminders of the universality of predation. No matter how strange the environment, life finds ways to consume and be consumed. The deep may lack sunlight, but it does not lack struggle. Here, as on land and in shallower seas, survival is contested, shaped by the interactions of hunters and prey. What differs is the form, the methods, and the adaptations, each moulded by darkness, pressure, and scarcity. As we continue downward and outward across the abyssal plains, these hunters remain part of the background of life. Their presence is constant, their forms varied, their strategies ingenious. But they are not the only source of light and signal in the deep. Beyond predation lies another kind of communication, another kind of adaptation. Creatures that speak not through sound or touch, but through glowing patterns written across their bodies. Ahead, the darkness reveals a new kind of language, one made entirely of light. The blackness of the deep might seem silent and empty to us, but for the creatures that live here it is neither. It is full of signals. Where voices and colours cannot travel, light becomes a language, crafted not by the sun but by the organisms themselves. Bioluminescence is not only a trick of survival or a lure for prey, it is also a way of communicating, of sending messages across the vast distances of darkness. In a world where encounters are rare and mates may be separated by kilometres of black water, these living flashes carry meaning as real as any spoken word. To understand how light can function as language, imagine what it means to live in the deep sea. Populations are sparse. Individuals may drift for days without encountering another of their kind. Sound carries, but not always in ways that can be finely tuned. Chemical signals spread, but they diffuse slowly, sometimes too slow to be useful. In this context, light provides an immediate, precise, and powerful form of expression. A flash can be seen instantly. A pattern can identify a species. A pulse can signal readiness to mate. Light becomes not only a tool, but a voice. Among the most common forms of this language are the photophores, the light-producing organs scattered along the bodies of fish, squid, and shrimp. Arranged in specific patterns, they serve as identifiers, much like fingerprints. A lanternfish, for instance, carries rows of photophores along its sides and belly. The arrangement varies between species, allowing individuals to recognize each other even in the blackness. For humans looking at these patterns, the differences might seem subtle. For the animals themselves, they are as clear as distinct markings. Recognition is essential because the risk of mistaking a predator for a mate is too great to ignore. Beyond recognition, light is also a means of attraction. Many deep-sea organisms use bioluminescence in courtship displays. Males may flash in rhythmic sequences, signalling to females of their species. Some patterns are steady pulses, others complex flickers. The details matter. The wrong rhythm or brightness may fail to elicit a response. In this way, bioluminescence becomes the equivalent of songbirds' calls or mammals' displays, a means of demonstrating presence, health, and suitability. In the emptiness of the ocean, where other forms of attraction are limited, this glowing language ensures that species can find each other across the dark. But bioluminescence is not always cooperative. It can be deceptive as well. Predators sometimes mimic the patterns of potential mates, luring individuals closer under false pretenses. In other cases, flashes are used to startle or mislead, sending mixed signals into the darkness. Just as language on land can carry lies, light in the ocean can carry falsehoods. The glow may promise safety but deliver danger. Some of the most intricate uses of bioluminescence are found in squids. These animals possess not only photophores but the ability to control them with remarkable precision. They can modulate brightness, duration, and sequence, producing complex displays that shift in real time. Some squids even combine bioluminescence with reflective tissues, creating patterns of light and dark across their bodies. These displays can confuse predators, attract mates, or signal aggression. To observers, the squid seems to shimmer with living code, a constantly shifting set of signals visible only to those who understand them. The vocabulary of this language extends to defense as well. Small fish, when threatened, may release bursts of light that function like emergency beacons, signaling to larger predators that another predator is nearby. This phenomenon, known as the burglar alarm strategy, turns the tables by using light to attract danger, not toward the victim, but toward its attacker. The sudden glow alerts larger hunters, who may swoop in on the scene, giving the smaller prey a chance to escape in the chaos. It is a risky tactic, but in the scarcity of the deep, risk often balances against survival. In some species, entire groups synchronize their light displays. Swarms of plankton or schools of fish may flash in unison, producing waves of illumination that ripple through the water. These collective signals may deter predators, confuse attackers, or simply overwhelm the senses of those watching. For us, seeing such a swarm is like watching a field of fireflies beneath the sea, a spectacle of coordinated communication that transforms the black water into a stage of movement and light. For the animals themselves, it is both protection and interaction, a form of social behaviour in an environment where direct contact is limited. Not all bioluminescent communication is visible to us. Some species emit in wavelengths that our eyes cannot detect, particularly in the red or infrared range. The dragonfish, for example, produces red light and has eyes adapted to see it. This allows it to send signals invisible to most other creatures. For them, this private channel of communication provides an enormous advantage. They can attract mates or illuminate prey without revealing themselves to competitors or predators. It is as if they carry their own invisible language, hidden in plain sight. The sophistication of these signals suggests that bioluminescence is not a crude adaptation, but refined one, developed and shaped over millions of years. Just as language on land has evolved in countless species, songs, calls, dances, so too has light become a form of expression underwater. Each species develops its own grammar, its own syntax of flashes and glows. To us they may seem like random bursts. To them, they are structured communication. Studying this language is a challenge. Observations require specialized equipment, as the presence of artificial light can overwhelm the delicate signals. Cameras must operate in complete darkness, capturing natural displays without disturbance. Even then, interpretation is difficult. We see the patterns but cannot easily decode their meaning. It is like hearing an unfamiliar language for the first time, recognizing that it carries information but not yet understanding the words. Over time, scientists are beginning to piece together fragments, identifying which patterns belong to which species, which flashes correspond to mating, which glows to defense. But the full lexicon of the deep remains beyond our grasp. What is clear is that this language of light is central to survival. In a place where a sound travels far but cannot always be fine-tuned, and where chemical signals spread too slowly, bioluminescence provides immediacy. It allows instant recognition, instant warning, instant connection. It reduces the uncertainty of the blackness, replacing it with flashes of meaning. Each glow is both an act of survival and an act of communication, carrying messages across the silence. Even the simplest displays remind us of how resourceful life can be. Consider a tiny copepod releasing a glowing trail as it flees. To us, it is a flicker, a line of light vanishing into the dark. To the copepod, it is a desperate message. Danger here, attention there, confusion created. The signal may last only seconds, but in those seconds it may mean survival. In this sense, every flash in the deep is a story, a moment of struggle, attraction, deception, or warning. It is also worth considering how this language shapes the perception of those who use it. For animals of the deep, the world is not empty, it is filled with signals we cannot see. To them, the black is dotted with points of reference, trails of light, pulsing patterns. Where we see nothing, they see a landscape of meaning. Their reality is not ours, shaped by a different form of communication, one that makes the deep not silent but alive. The role of bioluminescence in shaping ecosystems cannot be overstated. By enabling recognition, it allows species to find mates across vast spaces, ensuring reproduction in an environment where encounters are rare. By providing defense, it reduces losses to predation, stabilizing populations. By aiding hunting, it ensures the transfer of energy through the food web. Bioluminescence is not a decoration. It is an essential tool, a pillar of survival. Without it, the deep would be far poorer in life. For humans, the fascination with this living light is both scientific and aesthetic. Scientists study it to understand adaptation, communication, and biochemical processes. Engineers adapt it for imaging, sensing, and biotechnology. Artists and storytellers marvel at its beauty, weaving it into myth and metaphor, from the glow of plankton washing against a beach to the flashes of lanternfish miles below. Bioluminescence captures our imagination, because it feels like something alive that we can see only in glimpses. It bridges the distance between our bright world and the deep's hidden one. And yet, for the creatures of the abyss, it is not extraordinary. It is ordinary, the fabric of life itself. Just as we speak, gesture, or sing, they flash and glow. What we see as magic is to them routine. Their language is written in light, their survival carried by signals invisible to us, but omnipresent to them. As we continue through the deep, this language never disappears. It accompanies us, flickering at the edges of vision, illuminating encounters, shaping interactions. But beyond the signals of communication lies something even stranger. The traces of creatures whose presence is fleeting, rare, and sometimes barely real. Ahead, the darkness holds beings so elusive that they appear and vanish like ghosts. Reminders that in the ocean's ultimate depths, even life itself can feel like a haunting. In the deep sea, there are forms of life so elusive that even with all our instruments, we often glimpse them only for seconds before they vanish back into darkness. They're fragile, almost unreal, beings that appear more like drifting spirits than living animals. Their bodies are often transparent, their movements slow and dreamlike, their presence so fleeting that it is easy to believe they are more apparition than organism. To the human eye, accustomed to solid shapes and familiar textures, these creatures look like ghosts. In truth, they're not illusions at all, but some of the most refined survivors of the depths, evolved into forms that suit a world where weight, darkness, and scarcity strip life down to its essentials. Many of these ghostly beings belong to groups that rarely encounter the surface. Comb jellies, for instance, are among the most delicate of all deep-sea organisms. Their bodies are almost entirely water, transparent and gelatinous, with rows of tiny cilia running along their sides. As they move, these cilia scatter what little light exists into shimmering rainbows, producing iridescence that makes them look like drifting fragments of glass. They do not hunt with teeth or tentacles, but with sticky cells that capture plankton. In the blackness, their transparency makes them nearly invisible, a perfect camouflage against predators. They seem fragile to us, but that fragility is their strength. By being almost indistinguishable from the water around them, they survive unnoticed. Siphonophores are another group that inspire awe and confusion. They are not single organisms, but colonies, composed of many smaller individuals, each specialised for a task. Some parts provide flotation, others handle feeding, others reproduction. Linked together, they function as a single entity, stretching sometimes for tens of metres, longer than a blue whale. Their filaments dangle like curtains of glass, some glowing with bioluminescent sparks, others carrying stinging cells that paralyse passing prey. To watch one drift is to see a living chandelier, fragile yet deadly, a ghostly predator built from many parts that act as one. Certain jellyfish also embody this spectral presence. Some species from the deep are almost entirely invisible, except for faint glowing edges. Their bells pulse slowly, their tentacles trailing like threads that vanish into blackness. Others display sudden flashes of light when disturbed, as if announcing their presence for only an instant before fading again. To encounter them is to witness a moment of beauty that dissolves as quickly as it appeared. The deeper one goes, the more these apparitions dominate, reminding us that the ocean's largest habitat is filled with beings that defy our expectations of what life should look like. There are fish, too, that carry this ghost-like quality. The barrelly fish, for example, has a transparent head through which its eyes can rotate upward, scanning the silhouettes of prey above. The rest of its body is dark, but its head reveals organs and structures usually hidden inside. To see one is disorienting. It looks like something half real, half imagined. The transparency is not weakness, but adaptation. allowing light to pass through while protecting sensitive tissues. Its upward-gazing eyes, encased in a clear dome, are perfect for detecting the faintest glimmers in the water column. It is a hunter, hidden inside its own ghostly disguise. Other species achieve ghostliness through coloration. Many deep-sea creatures are coloured a translucent red or black. At these depths, red light does not exist, absorbed long before it reaches so far. To other animals, red is invisible, effectively turning these creatures transparent against the darkness. The red colour we see when brought to the surface is meaningless below. In their true environment, they are invisible, hiding in plain sight. To divers and explorers, they appear as faint shadows, almost insubstantial, drifting past without form. This ghost-like quality is not only visual but behavioural. Many of these creatures move slowly, conserving energy in the scarcity of the deep. They drift more than they swim, allowing currents to carry them. They do not rush or dart but hover, undulating gently, present one moment and gone the next. Some inflate or collapse, changing shape so dramatically that it is difficult to believe they are the same animal. Their fragility allows them to change fluidly, to adapt to the subtle shifts of water and pressure. The rarity of encounters adds to their ghostly reputation. Submersibles may spend hours in the dark without seeing a single creature, then suddenly be surrounded by drifting jellies, glowing siphonophores, or delicate transparent fish. Just as suddenly, they vanish, leaving only blackness behind. For those few who have seen them in person, the experience often carries a sense of unreality, as though the ocean revealed a secret briefly before closing it again. There is also the matter of survival in fragility. On land, we think of strength as protection, armour, teeth, speed. In the deep, fragility itself can be the strategy. Transparent tissues, delicate filaments, gelatinous bodies, all of these make animals harder to detect or less appealing to eat. Predators that swallow by volume may avoid creatures too watery to provide much energy. Fragile structures collapse harmlessly rather than resisting attack. What seems like weakness is a highly successful form of defense. Some of the most haunting creatures in this category are those that appear rarely even to science. A few gelatinous organisms have been filmed only once or twice, captured fleetingly by deep-sea cameras before disappearing forever. Each sighting is debated, classified and studied, but without repeated encounters, many remain mysteries. We know they exist, but their names, behaviours and lifespans are uncertain. They drift in and out of a knowledge like phantoms, reminders that the deep still holds secrets too delicate for our instruments to capture. Even the remains of life can take on ghostly forms. Carcasses sinking into the abyss often become stripped of flesh, leaving bones that glow faintly under microbial activity. Sometimes the outlines of once living animals are preserved as impressions in the sediment, shadows of bodies that vanished long ago. These echoes of existence fading in the silence add to the sense that the deep is haunted not by spirits, but by fragile records of life that pass quickly and leave faint traces. To call these creatures ghosts is, of course, a projection of our perspective. They are not apparitions, but living, breathing beings, perfectly adapted to their world. Yet the comparison persists because they defy our expectations. They lack solidity, speed, or form as we know it. They seem to fade into their surroundings to exist at the edge of perception. For humans accustomed to solidity, they feel like reminders of impermanence, of the thin line between presence and absence. And yet, despite their fragility, these beings play important roles in the ecosystem. Comb jellies consume plankton and regulate populations. Siphonophores control schools of small fish and crustaceans. Transparent fish like the barreleye maintain balance in the food web. Their presence may be fleeting, but their impact is real. They are not illusions, but pillars of the deep, quietly shaping survival in ways we often overlook. The presence of such creatures also highlights the limitations of our exploration. Many of them cannot be brought to the surface intact. Their bodies collapse under the absence of pressure, disintegrating into formless jelly. They can only be seen in their natural environment, in the deep where they belong. This makes studying them a challenge. Cameras and remote vehicles have given us glimpses, but much of their biology remains unknown. For every ghost we capture on film, there may be dozens more drifting unseen. Perhaps that is part of their enduring fascination. They remind us that most of the planet remains out of reach, inhabited by beings that seem more imagined than real. They show us that survival does not always take the form of strength or solidity. Sometimes it takes the form of fragility, transparency, and silence. Sometimes the best way to exist is to be barely there at all. And as we move further, past these spectral forms and into the wide plains of the abyss, another kind of presence emerges. It is not the fragility of ghosts, but the vast emptiness of landscapes that stretch beyond sight. Here, the ocean floor flattens into expanses where life thins, and the silence grows heavier. Ahead lies the domain of the abyssal plains, where distance and emptiness dominate, and where the deep continues its story on an even grander scale. As the journey sinks deeper, the drifting figures fade and the sense of space begins to change again. The feeling of weight remains, the darkness remains, but the terrain itself spreads out differently. Where before there were ridges, chimneys and drifting forms suspended in open water, now the seafloor emerges in broad, endless sheets. These are the abyssal plains, a realm that lies between 4,000 and 6,000 meters deep, covering more than half of the planet's surface. They are so vast that if the land were leveled, if every mountain and valley on Earth were smoothed into uniform ground, these plains would still dominate the world. They are the largest environment on Earth, yet they remain the least explored. To imagine them is to imagine emptiness. Not the emptiness of space dotted with stars, but the emptiness of distance stretched flat. They are covered in fine sediments that have accumulated for millions of years, dust settling into silt, forming soft carpets that smother every contour. Mountains may exist, but they are buried beneath layers of particles. Ridges may rise, but even they are softened by the endless rain of debris. The abyssal plains are deserts of mud, landscapes without horizon, their vastness accentuated by the absence of landmarks. The silence here is heavy. Sound travels, but it carries across flat surfaces without much reflection. Light does not reach. The only illumination comes from the occasional flicker of bioluminescence, brief and transient, swallowed almost instantly by blackness. Time itself seems slowed, because nothing here moves quickly. The water is cold and still, circulation sluggish, organisms deliberate in every action. Life on these plains is sparse compared to the zones above, but it exists in astonishing variety. Scattered across the sediment are sea cucumbers, echinoderms that crawl slowly, vacuuming detritus into their bodies. Some are transparent, their digestive tracts visible through gelatinous skin. Others are brightly coloured, odd bursts of pink or orange in the black. They process the sediment, filtering organic particles from the mud, playing a role as cleaners of the plains. Though unremarkable at first glance, they are among the most numerous of deep-sea animals, carpeting the seafloor in densities that make them vital to the ecosystem. There are brittle stars as well, relatives of sea stars, extending their arms outward like delicate spokes. They wave and twist, capturing fragments drifting in the current. Some bury themselves beneath the mud, exposing only their arms to feed. Others move slowly across the surface, leaving faint tracks in the sediment, trails that may last for months in the absence of disturbance. Crabs, amphipods, and small isopods scuttle among them, scavenging for scraps. Each footprint, each movement leaves an impression, evidence of life in an otherwise still environment. Occasionally larger creatures appear. Deep-sea octopuses glide across the plains, their arms trailing behind them like shadows. Some species have been observed brooding their eggs for years at a time, protecting them in the cold until they finally hatch. Sleeper sharks drift slowly above the sediment, their movements sluggish but persistent. They can survive for centuries, feeding opportunistically on whatever they find, from fish to carrion. Other sharks pass through as well, ghosts of predators in a realm that rarely sees their kind. Despite the apparent emptiness, the abyssal plains are shaped by the rain of organic matter from above. Marine snow continues its descent here, flakes of dead plankton, fecal pellets, fragments of animals. Most of it is consumed before reaching this far, but enough arrives to fuel the communities scattered across the mud. Sometimes larger events punctuate the monotony. A fish carcass, a squid, or even an entire whale may descend, settling onto the plain. These rare arrivals transform the landscape, attracting swarms of scavengers. Amphipods gather in dense numbers, stripping the flesh quickly. Fish, crabs and worms follow, feeding on leftovers. Microbes colonize the bones, releasing nutrients back into the environment. A single whale fall can become an oasis of life for decades, a localized ecosystem in a desert of mud. Beyond scavengers, microbes dominate the plains. They live in the sediments, feeding on the organic matter that accumulates over time. Some metabolize chemicals like methane or sulfates, playing roles in global cycles of carbon and sulfur. Their populations are immense, forming a microbial mat beneath the surface of the mud. Though invisible to us, they represent one of the largest reservoirs of biomass on the planet. They recycle nutrients, regulate chemistry, and support larger organisms indirectly. In many ways, the plains are their domain, and all else exists as guests above their microbial foundation. The abyssal plains are also dotted with unusual mineral formations. Polymetallic nodules, small potato-shaped rocks composed of manganese, nickel, cobalt and copper, grow slowly over millions of years as metals precipitate from seawater. They are scattered across the sediment like stones in a desert, each one taking millions of years to form just a few centimeters. For industry, they represent valuable resources, a potential source of metals for technology. For the ecosystem, they represent hard surfaces in a world of soft mud. Sponges, corals, and other sessile organisms anchor themselves to these nodules, creating microhabitats in an otherwise uniform landscape. Around each nodule, biodiversity increases, making them critical features in the ecology of the plains. The scale of these plains makes them difficult to comprehend. A single expanse may stretch for thousands of kilometers without significant variation. To walk across them would be to walk across monotony itself, each step identical to the last, with no landmarks to guide or break the journey. To drift above them in a submersible is to feel the immensity of Earth in a way no land environment can provide. Deserts, tundras, and ice fields are small by comparison. The abyssal plains are the true wilderness, covering most of the planet yet remaining nearly invisible to us. And yet they are not barren. They are punctuated by signs of activity, tracks left by sea cucumbers, pits dug by crabs, burrows made by worms. These traces can persist for years, preserved in the stillness of the sediment. They reveal the presence of life even when no animals are in sight, evidence that the plains are not empty but inhabited by creatures that move slowly, cautiously, and rarely. Every track, every mound, every disturbance is a signature of survival. Studying the abyssal plains has been one of the most challenging tasks for marine science. Nets often bring up mud with scattered creatures, but such collections cannot capture the full scale of the ecosystem. Cameras towed behind ships provide glimpses, revealing animals in their natural state. Autonomous vehicles and landers, equipped with lights and sensors, allow longer observations. Yet even with these technologies, we have mapped only small portions. The sheer vastness of the plains makes them elusive, a landscape so large that a lifetime of exploration could cover only fragments. The fragility of this ecosystem is a growing concern. Industrial interest in deep-sea mining has targeted the polymetallic nodules scattered across the plains. Removing them would not only strip resources that took millions of years to form, but also destroy the habitats they support. The sediment, once disturbed, could take centuries to settle. The slow pace of life here means recovery is not measured in years but in millennia. What looks like mud to us is in fact an ancient and delicate system, easily disrupted by the machines we design. To float above the abyssal plains in a submersible is to experience a paradox. The landscape appears featureless, monotonous, empty. But closer inspection reveals endless detail. The slow crawl of a cucumber, the faint ripple of a brittle star's arm, the sudden appearance of a scavenging crab. The emptiness is only an illusion created by distance. Life is everywhere, but spread so thin that only patient observation reveals it. The vastness magnifies the sense of isolation, but within it, every trace of life becomes profound. Perhaps what makes the abyssal plains most remarkable is their endurance. They have existed largely unchanged for millions of years. The sediments accumulate slowly, the creatures move slowly, the systems operate on timescales far longer than human lives. While the surface changes with seasons, storms and human activity, the abyssal plains remain steady, timeless in their silence. To witness them is to witness the deep time of Earth itself, a landscape that moves at the pace of geology rather than biology. As we continue across these vast expanses, it becomes clear that they are not the end of the journey but a stage along the way. Beyond them rise features more dramatic, vents where heat erupts into cold, trenches that cut even deeper, and ecosystems that flourish in defiance of expectation. The plains may be vast and lonely, but they are not lifeless, and they are not final. They are the foundation upon which the mysteries of the greater deep continue to unfold. The abyssal plains stretch for thousands of kilometres, flat and silent, but they are not without interruption. Every so often the monotony breaks. Cracks in the Earth's crust open where tectonic plates meet and separate, allowing seawater to penetrate deep into the rock. That water is heated by magma below, infused with minerals, and forced back upward into the ocean. Where it emerges, the landscape transforms from cold silence into something startling. Superheated fluids gush into the frigid water, carrying chemicals and metals that instantly solidify into towering structures. These are hydrothermal vents, fissures where Earth itself breathes fire into the abyss. The contrast is dramatic. Around the vents, the water can reach temperatures of more than 350 degrees Celsius, hot enough to melt lead at the surface, yet under immense pressure it remains liquid. Just a few meters away, the surrounding ocean remains close to freezing. The result is an environment of extremes where fire and ice meet in the dark. To human intuition, such conditions seem incompatible with life. But here, life is not only present, it is abundant. The vents support some of the densest communities in the deep sea, entire cities of life rising from the volcanic chimneys. At the heart of these communities are microbes. They do not rely on sunlight but on chemistry. Using hydrogen sulfide and methane spewing from the vents, they perform chemosynthesis, producing organic matter just as plants do with photosynthesis. These microbes coat the surfaces of chimneys, form mats across the seafloor, and live inside the tissues of larger animals. They are the foundation of food webs independent of the sun, proof that life can thrive wherever energy exists, no matter its source. Around these microbes gather animals found nowhere else. Giant tube worms are perhaps the most iconic. Growing up to 2 meters long, they form dense clusters that resemble forests of red-tipped stalks. They have no mouths or stomachs. Instead, they harbour symbiotic bacteria within their bodies. The bacteria use the vent chemicals to produce nutrients, which they share with their worm hosts. In this partnership, both thrive. The worms provide shelter and transport for the bacteria, and the bacteria provide food for the worms. Together they create a spectacle of life that seems impossible in such a place. Mussels and clams also flourish around vents, living in thick beds. Like the tube worms, many host symbiotic bacteria in their gills. They filter water not for plankton but for chemicals, feeding their bacterial partners who in turn feed them. Shrimp swarm across the chimneys, some with light-sensitive patches on their backs, to detect faint glow from the vents. Crabs scuttle among them, scavenging or preying on smaller creatures. Fish hover in the water, their presence a reminder that even in the deep, predators never disappear. The scale of these gatherings is astonishing. Where the abyssal plains are sparsely populated, vents teem with life. Densities can rival coral reefs in the shallows. Every surface is colonized, every crevice filled. Tube worms grow shoulder to shoulder, mussels pack tightly together, shrimp form restless swarms. It is a sudden explosion of vitality in an otherwise quiet world. The contrast makes the vents feel like oases in a desert, islands of abundance in a sea of scarcity. The structures themselves are equally striking. As the hot fluids cool, dissolved minerals precipitate, forming chimneys that can rise tens of meters above the seafloor. Some are black smokers, emitting dark plumes rich in sulfides. Others are white smokers, releasing lighter fluids with different chemical compositions. Over time, the chimneys grow, collapse, and regrow, shaping landscapes of towers, spires, and cliffs. They are not permanent but dynamic, always changing as the venting continues. Life here is tightly tied to this cycle. When a vent shuts down, its community eventually dies, deprived of chemical energy. But new vents open elsewhere, and life colonizes them again. Larvae carried by currents settle, bacteria establish themselves, and new cities form. The process is relentless, a cycle of destruction and renewal. In this way, vent communities resemble forests that burn and regrow, ecosystems shaped by disturbance as much as stability. Studying these vents has changed our understanding of biology. Before their discovery in 1977, it was widely assumed that all ecosystems ultimately depended on sunlight. The revelation that life could thrive entirely on chemical energy shattered that assumption. It showed that Earth harbours multiple independent strategies for survival. It also expanded the possibilities for life beyond Earth. If organisms can live here, sustained by chemistry alone, then perhaps they can live in the subsurface oceans of Europa or Enceladus, moons where liquid water meets volcanic rock beneath ice. Hydrothermal vents on Earth became not just discoveries but analogues for other worlds. The adaptations of vent animals are remarkable. Tube worms grow quickly, reaching full size in just a few years, an astonishing pace in the deep sea. Shrimp cluster near the hottest fluids, enduring temperatures that would kill most animals. Mussels withstand toxic sulfides that would poison other species. Microbes survive at temperatures once thought impossible for life, some reproducing at over 120 degrees Celsius. Each adaptation defies the limits we once believed were fixed. The abundance of life also supports unique interactions. Predators such as vent crabs and fish feed on smaller species, while scavengers take advantage of any waste or remains. Symbiosis dominates, with bacteria living inside worms, clams, and even shrimp. Some shrimp graze directly on bacterial mats, while others cultivate bacteria on their own bodies, scraping them off to eat. This intricate web demonstrates that even in extreme environments, ecosystems are complex and interdependent. The vents also reveal the resilience of life. They exist in places of constant instability. Chimneys collapse, flows shift, toxins rise and fall, yet the communities persist, rebuilding themselves again and again. Life here is not fragile but dynamic, thriving in turbulence. It suggests that life does not require stability to flourish. It requires only energy and opportunity. Human interest in these vents extends beyond biology. The mineral deposits they produce are rich in metals such as copper, zinc, and gold. As technology demands increase, some industries have looked toward vent fields as potential mining sites. But removing these resources would destroy the unique communities they support, ecosystems that may take millennia to re-establish. The vents are not just deposits of minerals, they are living cities, fragile and irreplaceable. Protecting them requires recognizing their value not in extraction but in knowledge. To witness a vent field is to witness one of the most alien landscapes on Earth. Towers of mineral rise into blackness, belching plumes of smoke that drift upward like chimneys. Around them, creatures cluster in densities unimaginable elsewhere in the deep. Tube worms sway in unseen currents, shrimp scuttle in waves, crabs climb among the spires. The scene is both surreal and vibrant, a contradiction of fire and water, death and life. In the silence of the abyss, the vents roar with activity, and yet, as abundant as they are, the vent cities are only pockets in the immensity of the deep. Beyond their glow, the plains stretch silent again, empty compared to the abundance concentrated around the chimneys. The vents remind us that life can flourish intensely in the harshest of places, but also that such flourishing is rare, tied to narrow circumstances. They are beacons in the abyss, proof that Earth's extremes are not barriers but stages for survival. As the journey moves on from these fiery cities, another kind of depth emerges. Beyond the oases, the seafloor plunges into trenches, cuts in the crust that reach deeper than anywhere else on the planet. Here, pressure intensifies beyond comprehension, and darkness becomes absolute. Yet even there, life continues, shadows breathing at the edge of possibility, waiting in silence. The vast plains and the fiery oases of vent fields are not the deepest places on Earth. Beyond them lie scars cut into the seafloor where tectonic plates collide, immense depressions that drop farther than Mount Everest rises. These are the ocean trenches, the Hadal depths, places that reach over 11,000 meters beneath the surface. They are narrow compared to the plains, covering only a fraction of the seafloor, but their depth makes them some of the most extreme environments on the planet. To enter them is to descend into a world where pressure rises to levels almost unimaginable, where darkness is absolute, and where life persists in forms we are only beginning to glimpse. The Mariana Trench in the Western Pacific is the most famous of these. Its deepest point, the Challenger Deep, plunges nearly 11 kilometers down. Few humans have ever seen it directly. The descent requires vessels engineered with extraordinary precision, their hulls spherical and reinforced, designed to resist pressures over 1,000 times greater than at the surface. Even the smallest flaw in construction would mean instant destruction. Yet life there has no such protection. It exists without armour, without steel, perfectly adapted to the crushing conditions. For the creatures of the trench, pressure is not a threat, it is the background of existence. The shadows that inhabit these depths are some of the strangest forms of life on Earth. Amphipods, shrimp-like crustaceans, thrive even at the greatest depths. They have been collected from trenches at nearly 11 kilometers, their bodies flexible and adapted to withstand the enormous pressure. Some grow larger than their shallow water relatives, a phenomenon known as deep-sea gigantism. Others remain small but swarm in dense numbers, consuming whatever organic matter sinks to the trench floor. Their resilience demonstrates that life can adapt even where conditions seem unbearable. Among the most remarkable trench dwellers are snailfish. These delicate translucent creatures have been recorded at depths over 8,000 meters, swimming gracefully through the blackness. Their bodies lack the rigid structures that would collapse under pressure. Instead, they are soft and gelatinous, perfectly suited to the environment. Their enzymes and membranes are adapted with unique chemicals that keep their cells functioning under extreme compression. To see one is to witness life in its most refined adaptation, fragile to our eyes but perfectly balanced against the weight of the ocean. The trench floor itself is stark and unsettling. It is not flat like the abyssal plains but sloped and uneven, carved by geological forces. Landslides and earthquakes shape its walls, sending cascades of sediment tumbling downward. Organic matter accumulates here, funneled from above, creating deposits richer than the surrounding plains. This concentration of material makes the trenches vital sinks of carbon, playing a role in Earth's climate systems. For the organisms that live there, the trenches are both a refuge and a trap, places where food may be more abundant but where escape is impossible. Even microbes thrive in these depths. Samples from trench sediments reveal microbial communities capable of metabolizing under immense pressure. Some survive by consuming organic matter, while others rely on chemical reactions with minerals. These microbes dominate the Hadal ecosystem, providing energy for larger organisms. Their ability to persist in such conditions has implications beyond Earth, suggesting that life could survive in high-pressure environments elsewhere in the universe. The trenches also host creatures so rarely seen that they feel almost mythical. Observations have revealed giant amphipods with armoured exoskeletons, strange worms that burrow in sediment, and translucent holothurians drifting just above the floor. Cameras deployed into the Challenger Deep have captured ghostly shapes moving across the mud, shadows that vanish before they can be identified. Each sighting adds to the mystery, reminding us that our knowledge of these depths is still fragmentary. The adaptations that allow life to breathe in these shadows are extraordinary. Proteins that would normally collapse under pressure are stabilized by molecules known as piezolites, which act like scaffolding inside cells. Membranes are built from special lipids that remain flexible despite compression. DNA repair mechanisms are enhanced, protecting organisms from stress. Reproduction is slowed, lifespans extended, and growth steady but deliberate. Each feature is tuned precisely to the environment, leaving no room for error. What would destroy us in seconds is ordinary for them. The scale of pressure here is difficult to convey. At the deepest points, it is equivalent to the weight of 50 jumbo jets pressing on every square metre. Human minds struggle to grasp it, and yet for trench creatures, it is unnoticed. They do not resist it. They exist within it as naturally as we exist in air. This reversal of perspective challenges our assumptions about the limits of biology. It suggests that life is not defined by comfort, but by possibility. Where there is energy, matter, and adaptation, life finds a way. Exploration of the trenches has been rare. The Trieste reached the Challenger Deep in 1960, carrying 2 men in a reinforced sphere. Decades later, James Cameron descended alone, capturing footage of the trench floor. More recently, robotic landers and submersibles have explored these depths, recording creatures and collecting samples. Each mission is a technical triumph, yet the vast majority of the trenches remain unseen. Their narrowness, remoteness, and depth make them the least studied regions of the ocean. What we know is a fraction of what exists, and yet, even in this fraction, the discoveries have been profound. The presence of complex animals at such depths was once doubted. Many believed that life could not exist beyond 6,000 meters. The discovery of amphipods and snailfish far deeper overturned that assumption. Each new sighting pushes the boundary of what we believe is possible. The trenches remind us that our knowledge of Earth is still incomplete, that even on our own planet there are frontiers untouched. The shadows of the trenches also highlight the fragility of this life. Because conditions are so extreme, these organisms cannot survive outside their environment. When brought to the surface, they disintegrate, their bodies collapsing without pressure to hold them together. This makes studying them difficult. We can see them in their home, but we cannot preserve them in ours. They exist in a world fundamentally separate from our own, connected by knowledge but not by direct experience. For all their strangeness, these trench dwellers play important roles in Earth systems. By consuming organic matter, they regulate carbon cycles. By burying material in sediments, they help sequester carbon for millennia. By metabolizing minerals, microbes influence the chemistry of the deep ocean. In this way, the trenches, though small in area, have global impacts. They are not isolated curiosities, but active participants in planetary balance. To imagine drifting in the trench is to imagine silence magnified. The walls rise above, the floor spreads below, the darkness has no gradient. Creatures appear only occasionally, faint and fleeting, breathing shadows that vanish quickly. It is an environment that feels more alien than any other on Earth, yet it belongs entirely to this planet. To witness it is to understand that Earth harbours worlds within worlds, each more extreme than the last. And beyond the trenches, the journey does not end. Other adaptations wait, shaped not only by depth and darkness, but by the physics of survival itself. The deep continues to reveal strategies that expand our sense of life's possibilities, showing us that existence is not fragile but endlessly inventive. Ahead lies an exploration of how survival is written into physics itself, how creatures endure not only pressure and darkness, but the fundamental constraints of energy and matter. The trenches reveal the extremes of pressure and darkness, but beneath those extremes lies something even more fundamental. Life in the deep is not only a matter of biology, it is also a matter of physics. The strange conditions of the abyss and the Hadal zones bend the rules in ways that challenge our assumptions. Temperature, pressure, buoyancy, chemistry, all of these are physical realities that living things must negotiate. Survival here is not a matter of brute strength, but of working with the laws of physics as they unfold in this alien environment. One of the most important forces is pressure. At the surface we move easily in air, our lungs filled with gases, our bodies supported by bones and muscles. In the depths, gases become a liability. Any air-filled space collapses under weight, and so life here abandons air altogether. Swim bladders, lungs, cavities, these are gone. Buoyancy is maintained not by trapped gas but by oils, wax esters, and gelatinous tissues. These materials resist compression, providing neutral buoyancy without risk. It is a fundamental rewriting of body design, shaped by physics as much as by evolution. But pressure does more than crush cavities. It alters the very chemistry of molecules. Proteins, the machines of cells, depend on their shapes to function. Under extreme pressure, those shapes distort, collapsing into forms that no longer work. Deep-sea organisms solve this by using molecules called piezolites, small compounds that stabilize proteins against compression. Trimethylamine oxide, or TMO, is one such molecule, accumulating in tissues in increasing concentrations the deeper an organism lives. It is a physical necessity. Without TMAO, proteins fail, but TMAO has a cost. At very high concentrations, it becomes toxic. This sets an ultimate boundary. Somewhere below the maximum depths of the trenches, pressure would require more TMAO than a body could tolerate. Life adapts, but physics sets the final line. Temperature also dictates survival. The deep ocean is cold, hovering just above freezing, except near hydrothermal vents. Cold slows chemical reactions, slows metabolism, slows growth. Proteins function less efficiently, membranes stiffen. To counter this, deep-sea organisms incorporate unsaturated lipids into their membranes, keeping them flexible at low temperatures. Their enzymes evolve to function in cold, sometimes at the cost of efficiency and warmth. The result is bodies tuned precisely to their thermal environment. If brought upward, many of these creatures cannot cope with higher temperatures, just as they cannot cope with lower pressures. Their survival is balanced delicately on physical conditions. Light is another physical limit. Sunlight disappears within a few hundred meters. By 1,000 meters, darkness is complete. For surface life, sight is the dominant sense. For the deep, light becomes both rare and precious. Bioluminescence emerges as the solution, a way to produce light where none exists. But even this is constrained by physics. Water absorbs different wavelengths of light differently, with red vanishing quickly and blue travelling farthest. As a result, most bioluminescence is blue-green. Only a few organisms break this rule, producing red or infrared light visible only to themselves. Even in adaptation, the physics of light shapes the vocabulary of survival. Energy itself is scarce. Without sunlight, ecosystems depend on the slow trickle of organic matter falling from above or on chemical reactions at vents and seeps. Energy density is low, and organisms must make the most of it. This physics of scarcity dictates slow metabolisms, long lifespans, delayed reproduction. It encourages gigantism in some species, fragility in others. It drives patience and opportunism. The flow of energy is physics at its most basic, and in the deep that flow is reduced to its thinnest stream. Life survives by tuning itself to that thinness. Even locomotion is shaped by physics. Water at these depths is dense and resistant, yet energy is precious. Fast swimming is rare, reserved for brief moments of predation or escape. Most movement is slow, deliberate, conserving energy. Bodies are streamlined not for speed but for efficiency, minimizing drag in a medium that punishes waste. Muscles are often flabby compared to shallow relatives, but this is not weakness, it is optimization. In a world where meals are rare, unnecessary expenditure is fatal. Another aspect is buoyancy itself. In the absence of gas-filled organs, bodies must achieve balance through density. Too heavy, and they sink irretrievably into mud. Too light, and they float upward, away from their habitat. The balance is delicate, maintained by tissue composition, oil deposits, and water-filled gelatinous structures. It is physics again, demanding precision, enforced with finality. The strange physics of survival also extends to reproduction. In shallower waters, eggs may float, larvae may disperse widely. In the deep, pressure and density make dispersal more difficult. Many species release fewer, larger eggs, investing in survival rather than numbers. Others produce larvae adapted to drift upward, settling in shallower waters before returning to the deep. Some reproduce rarely, with lifespans stretched across decades. These strategies reflect the cost of energy, the risk of dispersal, and the constraints of physics in a world where distances are immense and resources rare. Sound behaves differently here as well. In the deep, water transmits sound more efficiently than air. Whales exploit this, sending calls across entire ocean basins. Some deep-sea creatures may use sound at smaller scales, communicating or detecting prey through subtle vibrations, but the silence of the abyss remains striking because few animals make regular noise. The physics allows sound to travel far, but the scarcity of life and the energy cost of producing sound keep the depths mostly quiet. The chemistry of water under pressure also alters survival. Gases dissolve more readily, changing the balance of oxygen, carbon dioxide, and methane. Microbes exploit these changes using chemical reactions unavailable in shallower waters. Some oxidize methane, others reduce sulfates, still others metabolize hydrogen. These processes create energy flows that sustain entire ecosystems around vents and seeps. It is chemistry shaped by physics, and biology grows upon it. The limits imposed by physics are not only constraints but opportunities. Where pressure collapses proteins, organisms evolve stabilizers. Where light disappears, organisms invent bioluminescence. Where energy is scarce, they adopt patience and efficiency. Physics defines the stage, but life writes the script. The strange physics of survival is not simply about restriction. It is about innovation within boundaries. Every adaptation we see, the glowing lure of the anglerfish, the transparent body of the barrelé, the sprawling colony of the siphonophore, is a negotiation with physical law. For humans, these constraints are barriers. Pressure crushes our machines, cold limits our endurance, darkness blinds us. But for the creatures of the deep, these are not barriers. They are the ordinary fabric of life. This inversion of perspective is perhaps the most profound lesson. What we see as hostile, they see as normal. What we see as impossible, they embody without effort. And yet, even within these adaptations, there remain limits. Piécelites stabilize proteins, but only so far. Light can be produced, but only in certain wavelengths. Energy can be harvested, but only from the flows available. Physics sets boundaries that biology cannot cross. There is a point where pressure becomes too great, temperature too extreme, energy too scarce. Life adapts, but not without limit. The trenches may represent the farthest edge of what Earth allows. Beyond them, perhaps, there is only silence. But within those limits, the strange physics of survival has produced some of the most remarkable forms of life on Earth. Creatures that glow, creatures that expand their jaws to swallow prey half their size, creatures that drift like glass, creatures that survive in boiling vents or crushing trenches. All of them are examples of what is possible when life negotiates with physics rather than defying it. And as the journey continues deeper into understanding, the next realization emerges. Survival here is not just about individuals, it is about systems, about the circulation of nutrients, the cycling of carbon, the networks that link even the most remote organisms to the planet as a whole. Beyond physics lies connection, the unseen web that ties the ultimate depths to the surface world in ways that shape the entire Earth. The deep ocean is not only a place of extremes, it is also a place of time. When you travel downward through its layers, past the zones where light vanishes and pressure mounts, you enter an environment that has existed largely unchanged for millions of years. The conditions here are steady, unshifting and constant in a way the surface world has never been. On land, mountains rise and erode, forests appear and disappear, glaciers advance and retreat. In the shallow seas, temperatures rise and fall, storms sweep across the surface, and currents stir waters from season to season. But in the deep, the water remains near freezing, the darkness unbroken, the pressure eternal. It is a realm that preserves a memory of Earth's past, holding records in its sediments and in the slow persistence of its creatures. Every flake of marine snow that settles onto the seafloor carries with it a fragment of history. Tiny shells of plankton, fragments of organic matter, dust blown from continents, all drift down over centuries, layering into sediments that record climate, chemistry, and even volcanic eruptions. Cores taken from the seafloor reveal timelines stretching back tens of millions of years. They preserve ancient atmospheres captured in microscopic shells. They preserve evidence of mass extinctions, times when life faltered and oceans changed. They preserve traces of evolution, the rise and fall of species. The deep is not just a present environment, but an archive, a library of Earth's memory written in silt. For the organisms that live here, time moves differently as well. Many deep-sea species grow slowly, reproduce infrequently, and live for centuries. Greenland sharks, found in the cold waters of the North Atlantic and sometimes descending into deep layers, may live for over 400 years. Some corals, anchored to the seafloor in the dark, have lifespans stretching past 1,000 years. Sponges grow in reefs that may persist for tens of thousands of years. These creatures embody deep time, their lives overlapping generations of human history in ways we cannot easily comprehend. Where surface life is brief and fast, the deep moves at a scale of centuries and millennia. The stability of the deep also preserves evolutionary pathways. Many organisms found here resemble ancient forms, survivors of lineages long vanished from the surface. Some deep-sea fish retain primitive features, unchanged for millions of years. Horseshoe crabs, though not exclusive to the deep, share ancestry with creatures that thrived hundreds of millions of years ago. Certain deep-sea worms resemble fossils from the Cambrian period, suggesting that the deep has acted as a refuge for ancient lineages, a museum of living history. The conditions have remained stable enough to allow survival, where surface environments have shifted too quickly. Even the chemistry of the deep holds memory. Layers of sediment reveal fluctuations in carbon dioxide, oxygen, and nutrient levels that correspond to global changes. The abyssal circulation of water, the global conveyor belt, stores heat and carbon for centuries before releasing them again. A single molecule of water sinking into the North Atlantic may not surface again for 1,000 years. The deep is a reservoir of climate, moderating swings, absorbing shocks, and recording change in its currents. It is a system that remembers, not in conscious thought, but in the persistence of process. The creatures that inhabit these depths are also reminders of ancient survival. They are not modern novelties, but continuations of strategies that have worked for eons. The anglerfish, with its bioluminescent lure, represents a predatory design that has persisted for tens of millions of years. The giant isopod, with its armoured body, resembles forms from the Paleozoic. The coelacanth, once thought extinct, was rediscovered in deep waters, a living fossil that has survived for over 400 million years. These beings are not just adapted to the present, but carry the imprint of deep history. The deep also holds memory of catastrophic events. Mass extinctions leave their signatures in the sediments, iridium layers from asteroid impacts, carbon isotope shifts from volcanic upheavals, sudden disappearances of species in the fossil record. Each layer is a page in Earth's story, preserved by the stillness of the abyss. On the surface, erosion erases records, tectonics recycles crust, forests burn and ice melts. In the deep, sediment falls and remains, layer upon layer, holding memories the surface cannot. To drift through the deep is to move through this archive. Every particle, every organism, every current is a fragment of time extended. The silence, the cold, the darkness, all are reminders that the deep does not change with seasons, storms, or years. It changes only with epochs. It is a space where time itself stretches, not in perception, but in process. What happens here endures longer, moves slower, and records more. For humans, encountering this ancient memory is both humbling and unsettling. Our lives are short, our civilizations brief compared to the lifespan of a deep-sea coral. Our archives, our libraries, our monuments are fragile, vulnerable to destruction within centuries. The deep keeps its memory without intention, without effort, simply by existing as it does. It is the endurance of stillness, the permanence of constancy, that makes it the greatest archive of Earth. Even the organisms themselves embody memory in their adaptations. Bioluminescence, a trait common in the deep, is ancient, present in lineages that diverged hundreds of millions of years ago. Chemosynthesis, the process that sustains vent communities, may mirror some of the earliest energy pathways used by life on Earth. The molecules that stabilize proteins under pressure may hold clues to the origins of life itself. In this way, the deep is not only a memory of Earth's history, but a memory of life's beginnings. Studying the deep gives us access to this memory. Sediment cores reveal climate history. Genetic analysis of deep-sea organisms reveals evolutionary persistence. Chemical studies of vent microbes reveal pathways that may have been present in the earliest cells. Each discovery is not just about the present deep, but about the deep past. Each layer, each organism, each adaptation is a fragment of Earth's memory, preserved in darkness until revealed. The persistence of this environment also suggests something about the future. As the surface changes under human influence, warming oceans, shifting currents, rising carbon, the deep records and responds slowly. It will carry the memory of our era in its sediments and in its chemistry. Tens of thousands of years from now, future scientists, human or otherwise, will be able to read the story of our impact written in the abyss. The deep does not forget. It records without judgment, without bias, a silent ledger of all that falls into it. To think of the deep as memory is to recognize that time flows differently across environments. For us, a century is long. For a coral colony, it is a fragment. For sediments layered over millions of years, it is nothing. The deep reminds us that Earth does not share our scale of time. It moves slower, broader, deeper. Its memory is vast because its processes are vast. To glimpse it is to be reminded of our brevity, but also of our place within a much older continuum. And as we move onward, beyond the recognition of memory and into the myths humans have built to describe what they cannot see, the story takes on another layer. The deep is not only an archive of geology and biology, it has also been a canvas for imagination, a place where mystery has become story, where the unknown has given rise to monsters and legends. Ahead lies not just the memory of Earth, but the memory of humanity, recorded in the myths we tell about what lives in the black. For as long as humans have lived near the sea, the unknown beneath its surface has stirred imagination. The deep, invisible to the eye and unreachable until very recently, has always been a place where mystery accumulates. We cannot look directly into it, so we fill it with stories. Myths of sea monsters, tales of ghostly ships, legends of giant serpents. All of these are human attempts to describe a realm we could not enter. The ocean became both a source of sustenance and of fear, a boundary between the known and the incomprehensible. The deeper the waters, the greater the mystery and the darker the legends. Some of the earliest myths describe the sea itself as a monster. In Mesopotamian tradition, the primordial goddess Tiamat embodied the ocean's chaos, a vast and uncontrollable force that had to be subdued. In Norse mythology, Jörmungandr, the world serpent, circled the earth beneath the sea, so massive that its body encircled the planet. To the Polynesians, the ocean was both provider and danger, home to deities and spirits that governed tides and storms. In all of these stories, the ocean's depths were not empty. They were inhabited by beings as vast and unfathomable as the waters themselves. Sailors throughout history added their own layers to these myths. As they travelled farther from shore, into waters where the horizons stretched endlessly and the bottom was unimaginable, they began to report encounters with strange creatures, giant squids dragging ships beneath the waves, enormous whales mistaken for islands, serpents rising from the depths, their bodies undulating like waves. Some of these accounts were exaggerations of real animals, glimpses of whales, oarfish, or squid magnified by fear and uncertainty. Others were inventions, born from the human tendency to populate the unknown with figures of wonder and terror. The kraken is one of the most famous examples. Described in Scandinavian tales as a creature so large it could engulf entire ships, the kraken was said to dwell in the deep, rising occasionally to the surface to feed or to drag sailors down. Modern science has connected these stories to giant squid, real animals that can reach lengths of over 10 meters, with eyes the size of dinner plates. For centuries they were almost never seen alive, only encountered as carcasses washed ashore or as remains inside whale stomachs. Their elusiveness reinforced the myth, making them seem more monstrous than real. Even today, to see one alive in the wild is rare, reminding us that the roots of myth are often grounded in truth. Other legends speak of ghostly lights in the water, seas that glowed at night, frightening sailors who thought they were sailing into fires or spirits. We now know these were caused by bioluminescent plankton, disturbed by waves or ships, releasing flashes of light. But to those without knowledge of chemistry, the glowing ocean must have seemed supernatural. Even now, when we understand the cause, the sight of a bioluminescent beach can feel magical, as though the myths never really left. The mysteries of the deep also fueled tales of lost worlds. Atlantis, the fabled sunken city described by Plato, became a symbol of civilization swallowed by the ocean. Whether real or not, it reflected humanity's sense that the sea hides secrets, that entire histories could vanish beneath the waves. Similar myths appear in other cultures. Islands that sink and reappear, lands lost to floods, kingdoms hidden in trenches. These stories reflect not just imagination, but the reality that the ocean has always claimed land through storms, tsunamis and rising tides. The myths gave shape to the fear that the sea could erase as easily as it could provide. Sea serpents appear across cultures, from the Mediterranean to the Pacific. long undulating creatures sighted on the surface of the water, described as longer than ships, with heads like dragons. Many of these accounts likely came from oarfish, the world's longest bony fish, which can reach lengths of 11 metres and swim near the surface. Their ribbon-like bodies and undulating motion resemble the serpents of legend. When one appeared near shore, it would confirm centuries of stories. In Japan, oarfish are still seen as omens of earthquakes, messengers from the deep. But not all monsters of the deep were threats. Some myths describe guardians, protectors, or spirits of the ocean that guided sailors. Polynesian navigators invoke the spirits of the sea for safe passage. In Greek mythology, Nereus and the Nereids were benevolent figures embodying the gentler aspects of the ocean. Even in stories of danger, the sea was not only an enemy, but a force to be respected, a partner in survival. Its mysteries inspired reverence as much as fear. As science advanced, many of the monsters dissolved into natural explanations. Whales breached, squid tangled with ships, sharks grew to immense sizes. The sea serpents and krakens became understood as oarfish and giant squid. The glowing waters became bioluminescence, yet the mystery did not disappear. It only shifted deeper into places we could not yet reach. The trench floors, the abyssal plains, the black smokers, all remained hidden, leaving room for imagination to persist. Even now, with submersibles and cameras, the deep still inspires mythic language. We describe creatures as alien, ghostly, monstrous. We call the vents cities, the jellies spirits, the hunters unseen. These words reflect not only the strangeness of the animals, but our human need to make sense of them through story. The deep resist full comprehension, and so we continue to tell tales. The persistence of monsters in our imagination speaks to something deeper, our relationship with the unknown. Where knowledge ends, myth begins. The deep ocean has always represented the ultimate unknown, the greatest unexplored space on our planet. In its darkness, we projected our fears, our wonders, our possibilities. The monsters are not only reflections of real creatures, but of ourselves, of our need to personify mystery. In a sense, the monsters were never entirely wrong. The deep does hold creatures beyond our imagination. Anglerfish with lures, gulper eels with jaws that unhinge, siphonophores stretching for tens of meters, snailfish living at pressures that crush steel. They are not the dragons of legend, but they are no less remarkable. The reality, as it often turns out, is stranger than the myth. The monsters we invented pale beside the adaptations life has achieved. And as we think of myths, we also think of mystery itself. The ocean remains more mapped than explored. We have more detailed images of Mars than of the deep sea floor. The creatures we know are a fraction of those that exist. Thousands of species remain undiscovered, each with adaptations that could astonish us as much as any myth. The mystery is not a relic of the past. It is alive, waiting in the black water. The role of monsters in this context is not to deceive, but to remind us that mystery persists, that imagination is part of exploration, that to tell stories of serpents and krakens is to admit that we do not yet know everything, and that perhaps we never will. The deep invites not only science, but wonder. It needs both, because without wonder, discovery loses its meaning. As we drift further into these reflections, it becomes clear that the deep is not only about survival, adaptation, or myth. It is also a mirror. The stories we tell about it are as much about us as about the sea. The monsters reveal our fears of the unknown, our awe at vastness, our awareness of fragility. They show that we have always sensed the ocean as more than water. It is a force, a keeper of secrets, a presence beyond comprehension. And beyond the myths and monsters, the deep also carries lessons about life itself. It shows us how fragile we are compared to its endurance, how small our span of knowledge is compared to its mysteries. The monsters we once imagined are replaced by real creatures, and the myths we once told are replaced by science, but the sense of wonder remains. Ahead, what we learn from the deep is not about dragons or serpents, but about ourselves, about what survival means, and about how the unseen parts of Earth can shape our understanding of life. The deep sea is not only a habitat for creatures beyond imagination, it is also a reflection of the human condition. When we look into the black water, when we send machines to explore its unseen landscapes, we are not just studying alien ecosystems, we are also confronting our own place in nature. The deep, with its silence and enormity, reveals truths about survival, fragility, patience, and endurance that apply as much to us as to the animals that live there. One of the first lessons is humility. The deep reminds us that our world is larger than we can easily conceive. We often behave as though we know the planet, as though our maps and data give us mastery over it. Yet more than half of Earth's surface lies in the abyss, still unmapped, still unseen, still unknown. We have walked on the moon, we have sent probes beyond the solar system, but we have barely touched the deep ocean. To confront that reality is to accept that knowledge is always partial, that mystery remains immense, that our sense of control is often an illusion. The deep also teaches us about endurance. Life here persists under pressures and conditions that would crush us instantly. Creatures survive not by defiance but by adaptation, reshaping themselves to match the environment. They do not resist the weight, they become part of it. For us, this is a lesson about flexibility. Survival is rarely about overpowering the environment. It's about working within limits, adapting rather than resisting, finding ways to exist in harmony with forces larger than ourselves. Patience is another lesson. Many deep-sea species live slowly. They grow over decades, reproduce rarely, and endure long intervals without food. In our lives, defined by speed and immediacy, this slowness feels alien. Yet it demonstrates that survival does not always require haste. Sometimes it requires waiting, conserving, moving only when necessary. In the deep, impatience is wasteful. Energy must be guarded, used wisely, never squandered. There is wisdom in restraint, a reminder that time can stretch far longer than we imagine. The deep also shows us the value of cooperation. Vent communities, for instance, are built not by solitary individuals but by partnerships. Tube worms and bacteria share resources, each providing what the other cannot. Mussels host microbes in their tissues, shrimp cultivate them on their shells. Entire ecosystems thrive because of symbiosis. For humans, this is a reminder that independence is rarely absolute. We too depend on unseen partnerships, on microbes in our bodies, on plants that produce our oxygen, on societies that provide our survival. The deep makes this interdependence visible in dramatic ways. There is also a lesson about fragility. The ecosystems of the abyss are ancient, slow and delicate. Disturb them, and recovery takes centuries or millennia. A coral reef in the deep may have grown for thousands of years, only to be destroyed in minutes by human activity. A sediment plain may hold stable communities, disrupted forever by mining machines. These realities remind us that our actions carry consequences far beyond our lifetimes. The deep teaches us that endurance does not mean invulnerability. Even the most stable systems can be broken if we are careless. Mystery itself is a lesson. The ocean resists full understanding. Every expedition reveals new species, new adaptations, new questions. For us, accustomed to believing that knowledge is finite and complete, this is a humbling reminder that the unknown will always exceed the known. The deep teaches us to embrace uncertainty, to find wonder in not having all the answers, to accept that mystery is not failure, but part of existence. The strange adaptations of deep-sea creatures also mirror aspects of ourselves. The anglerfish lures prey with deception, reflecting how survival sometimes involves trickery. The gulper eel swallows what it can when it can, showing how scarcity shapes behaviour. The siphonophore is a colony of individuals functioning as one, echoing the way human societies depend on cooperation and specialisation. Each organism is not only a curiosity but a metaphor, a way of seeing our own strategies reflected in alien forms. There is a deeper philosophical lesson as well, that limits define possibility. Physics sets boundaries in the deep just as it does in our lives. Pressure, temperature, energy, these cannot be ignored. Life succeeds not by breaking limits but by finding ways within them. For humans, who often imagine themselves boundless, this is a reminder that constraint is not the end of possibility but the beginning of creativity. Every adaptation we see in the deep is creativity within limits. Our own survival, too, depends on respecting boundaries, whether of ecosystems, resources, or time. The deep also forces us to confront scale. In its vastness, we see how small we are. In its timescales, we see how brief we are. In its patience, we see how hurried we are. This confrontation is not meant to diminish us but to place us in context. We are part of a planet far older and larger than ourselves. The deep teaches perspective, the ability to see beyond our own urgency and recognise a broader, quieter continuity. Even the myths we create about the deep reflect something about us. When we imagine monsters in the ocean, we are not only projecting fear of the unknown, but also expressing our sense of vulnerability. When we invent cities like Atlantis, we are acknowledging our fear of loss, our awareness that what we build can be erased. The monsters and mysteries say less about the ocean and more about our own minds, our own attempts to give shape to uncertainty. In this way, the deep teaches us about imagination itself, about the stories we tell when knowledge ends. The patience of exploration is another lesson. Every discovery in the deep has come through years of preparation, through careful design, through persistence against failure. Cameras fail, submersibles crack, samples collapse. Progress is slow, but it accumulates. This mirrors how human knowledge advances, not in leaps but in increments, through patience and resilience. The deep demands humility not only in what it contains but in how we approach it. For many, the deep also stirs an existential lesson. To descend into blackness, to confront silence and vastness, is to feel the limits of human existence. It evokes both fear and awe, the recognition that we are small and temporary. Yet it also evokes connection. The same ocean that touches the trench floor touches our shores. The same processes that shape the abyss shape the air we breathe. We are not separate from the deep. We are linked to it through cycles of carbon, oxygen, and water. The lesson here is unity, that even the most remote parts of Earth are tied to us, and we to them. Perhaps the greatest lesson is resilience. The deep is harsh, unyielding, and extreme, yet it is full of life. Creatures thrive not in spite of the conditions, but because of them. This resilience is a reminder that survival is always possible, even in the darkest places. It tells us that life is not fragile in the way we imagine. It is inventive, persistent, capable of finding pathways through impossibility. When we face our own challenges, the deep reminds us that adaptation is always possible, that limits are not the end of life but the beginning of transformation. And as the narration drifts toward its next turn, what lies ahead is reflection, not only on what the deep reveals about the planet, but about intimacy itself. Because at the end of this long journey downward, the ocean does not simply remain remote and alien. It becomes personal, connected, a reminder of how the hidden parts of Earth echo within us. The deep is not only out there, far away, it is also within us, shaping the air we breathe, the stories we tell, the way we see ourselves. When you think about everything that lies beneath the surface, it becomes harder to see the ocean as only a boundary between shores or a space for travel and trade. The deep is not only geography, it is a part of the planet's beating heart, a reservoir of memory, mystery, survival, and imagination. and as much as it feels distant, far away, unreachable, it is never separate from us. The same currents that circulate through the abyss eventually touch the water that laps at coasts. The same oxygen produced by plankton near the surface depends on cycles that carry nutrients upward from the dark. The carbon buried in trench sediments balances the atmosphere we breathe. Every breath, every meal, every moment of life on land is tied to processes that unfold in silence miles beneath our feet. To reflect on this is to realize that the ocean's hidden depths are not only a scientific frontier, but a personal one. They remind us of how much of ourselves we still don't understand. We are accustomed to thinking of survival as a matter of control, of bending the world to fit our needs. But the creatures of the deep survive by blending with their environment, by becoming indistinguishable from the forces that shape them. Some disappear into transparency, others cultivate light in bodies built for blackness. Some stretch across enormous distances as colonies of individuals acting as one. Each of these strategies is alien to us at first, but they are not only about the ocean, they are about what it means to exist in a world that does not bend to our will. They are lessons we can choose to carry quietly, reminders that adaptation is sometimes more powerful than control. There is also something deeply human about the way we approach the unknown. For centuries, the deep was a source of fear. We filled it with monsters because we could not imagine it empty. We invented serpents and krakens because the human mind struggles to accept blankness. In a sense, these inventions say more about us than about the ocean. They reflect our inability to tolerate mystery without giving it shape. And yet, even now, when we have lights, cameras, submersibles, and samples, the mystery persists. We do not need to imagine monsters anymore, because the real creatures of the deep are strange enough to remind us that imagination and reality often converge. The deep gives us permission to wonder, to admit that not everything can be explained, not everything must be mapped, not everything will be revealed. And when you look closely at the patterns, the deep becomes something more intimate still. The slow patience of life on the abyssal plains mirrors the patience required in our own lives, the ability to wait for what comes rather than rushing to consume. The fragility of transparent creatures reminds us that weakness can be survival, that to be unnoticed can be safer than to be strong. The cooperation of vent communities, where bacteria and worms build partnerships that sustain entire cities, reminds us of how much we rely on one another. The shadows in the trenches, breathing silently at the limits of possibility, show us that even in the heaviest conditions, existence is possible. These are not only scientific facts, they are reflections, mirrors that let us see ourselves from another angle. The deep also forces us to confront time differently. We live in days and years, in memories that last decades. But the ocean floor holds records stretching back millions of years, sediments that archive every shift in climate, every extinction, every surge of life. Creatures here live centuries, even millennia. For them, our civilizations would pass like brief flashes of light in darkness. To see this is to be reminded that our sense of permanence is fragile, that what feels long to us is brief against the measure of Earth. And yet, that brevity does not diminish us. It gives weight to our moments, value to our choices. The deep teaches us that time is both vast and immediate, that our lives are small but still woven into the larger memory of the planet. In the stillness of the abyss there is also a kind of honesty. The ocean does not flatter us. It does not bend to our will. It continues on its own scales of time and pressure and silence. And yet, within that indifference it provides what we need. It circulates carbon, moderates climate, supports food webs, balances the planet. It doesn't do this for us, but we benefit nonetheless. To see the deep is to see the reality that we are always part of something larger, something that does not notice us and yet sustains us. This perspective can be unsettling, but it can also be grounding. It strips away illusion and reminds us of connection. When people descend into the deep, whether through a submersible window or through footage brought back from a camera, the reaction is often the same. Awe, but also stillness. The sight of a siphonophore stretching like a thread of glass. The sudden flash of a dragonfish's lure. The slow crawl of a sea cucumber across a plain of mud. These are not dramatic spectacles by the standards of surface life. They're quiet, deliberate, patient. And yet they stir something profound. They remind us that the planet is larger than our immediate concerns, that beauty exists even in silence and absence, that survival is everywhere, even where we least expect it. To sit with that realization is to understand that the deep is not alien to us. It is a part of the same earth that gave rise to us. The water in our bodies, the salts in our blood, the rhythms of our biology all echo the ocean. Our earliest ancestors emerged from its shallows, shaped by its chemistry and cycles. In a sense, the deep is not distant but ancestral. It is a hidden inheritance, carried forward in every cell. To feel this connection is to see the ocean not only as environment but as origin, not only as unknown but as memory. The idea of the ocean as a secret heart becomes clearer in this light. It beats beneath us, regulating the planet's systems, circulating energy, balancing forces. It holds memories older than our species, perhaps older than life itself. It shelters creatures that seem impossibly strange, yet perfectly adapted. It persists in silence, reminding us that life is not always noisy or visible or fast. It is steady, patient, enduring. And even if we never descend to its greatest depths, we are connected to it in every breath and every moment. To bring this thought closer, consider the quiet question of perspective. The ocean does not ask us to control it. It asks us to recognize it, to respect it, to see its role in our survival. It teaches us by existing as it does, without compromise, without apology. The question is whether we are willing to listen. If we are, then the deep offers more than mystery. It offers humility, perspective, connection, and perhaps even comfort. And as you sit here listening, you are part of this story as well. You do not need to be at the bottom of a trench or beside a vent to feel the connection. You're already tied to the deep through every cycle of water, through every molecule of oxygen, through every grain of salt in your blood. The deep is not separate. It is present in you as much as it is present beneath the waves. That presence is the ocean's secret heart, beating silently beneath the surface, steady and enduring, a reminder that even the most hidden parts of Earth are never truly far from us.